we measure them, and then how we collect data using a questionnaire. Okay, so at the end of the day, you want to look at the various forms of measurement scales that we have. We will list the source of data we can use for research, describe the various ways of collecting data or data collection. So before we get there, first of all, we want to distinguish between two things. One we call experimental units, and another we are calling the variables, right? But before we get to those two distinctions, we want to talk about statistics. Generally, what is statistics? Statistics is about your ability to collect data, you organize the data, you present the data, you analyze, and then you interpret. And you are using it to assist in a more effective decision. You are making a decision not on a blind side, but with data and some numbers to be able to tell your left from your right and make an effective decision. That's what statistics is about. Okay, and we call it a science of data. At the end of the day, we rely on facts and figures, not based on our own subjective feelings. So statistics is about data and it's objective because it's based on facts and figures to make our informed decisions. Okay, now we are saying that when researchers are collecting the data, they collect the data which are some characteristics of objects or people or things of interest to them. And so those objects or those people or those, whatever they are interested in collecting data about, they are called experimental units. So if I'm interested in finding out about school feeding program and I go and I interview students, the students I'm interviewing are my experimental units. Okay, if I'm a scientist, marine biologist, I want to look at sharks in the ocean or whatever it is. The sharks are my experimental unit, so it's not necessarily humans. It could be houses, it could be trees, it could be anything that is of interest to the researcher where I'm gathering information about. That's what makes the experimental unit. Okay. And then whatever I'm going to measure on these experimental units are what we call the variables. So if it's about students and I'm going to ask for their age, then age becomes a variable. If I'm going to ask about their height, if I'm going to ask about the number of times they eat when they go to school, if I'm asking about their BEC results, all of these are variables because it's a measurement that we are taking from the experimental unit. So that's the difference between the two. Experimental units are the ones or the objects or the items that we are taking data on. The variables are what we are measuring on those particular experimental units. Okay, so get the distinction. Now we have types of data or types of variables, you can call it that way. So we have qualitative data or qualitative variables, and we have quantitative variables. So let's start with the qualitative. Qualitative variables are the ones that are just describing a characteristic about something. Okay, so normally it's an attribute, your hair color, your eye color, okay, those sort of things. It's a description, right? Are you male or female? Are you Catholic or Methodist? Are you a Muslim or are you a Christian? All of these are attributes or characteristics about the variable or the sort of experimental units you are looking at. Okay, so all of these are non-numeric. They are not numbers. You cannot find the mean of eye color among students. You can't do that. Or find the mean of religious affiliation. You can't find that. Once you can't do these sort of mathematics, basic mean, median, mode sort of thing on a variable, that variable is a qualitative variable. Okay, so marital status. I'm married, I'm single. We can't find the mean of marital status. And funny enough, some students will do and get means of some of these variables and describe. So these are qualitative variables. And so we can't have it being numeric. It's not, it's non-numeric. On the other side, quantitative variables are numeric variables. Okay, the variables that has numbers, They are variables that we can manipulate or do some statistics on. We can find the mean of that, median, we can find the standard deviation, variance. We can find all of these on particular quantitative variables. Example, age. We can find the average age of a class. We can find the average distance you cover to school. What is the average amount you spend on in a day? All of these become quantitative variables because they are numbers and you can do some mathematical items on them. Okay, so briefly, that's the difference between the two. One is non-numeric, the other is numeric. And under quantitative variable, we have two of them. We have discrete variables and we have continuous variables. Now, discrete variables, we say that they assume only certain values, and there are usually gaps in those values. And sometimes we call them countable variables. And so if I ask you, how many times did you visit the hospital in a year? You are just going to say once, twice, or 5 times, or 10 times in a year, or once every month and stuff like that. These are counts. They are countable. I'm not sure if you say I visited the hospital 1.5 times. I'm sure people will laugh at you because why 1 point, what does it mean to say 1.5 times? It doesn't make sense. How many bedrooms do you have? And you say I have 3.25 bedrooms. It doesn't make sense, right? How many cars can you see here? You say 2.5 cars or 7.5 cars. Those are telling you that they cannot assume those decimals. So that particular kind of variable, if you are measuring that kind of variable, they can only be discrete quantitative variables. They are counts. You can only count 1, 2, 3, 4, and there are no decimals in there. They are only counts. They cannot assume a decimal. Okay, so discrete variables are variables that are measured in this manner. They are in the form of a count. Whilst continuous variables assume every little detail. It can take any decimal. It can be 12.397, whatever it is. It can assume those values. So there are no gaps in them. You can't start from 1 and jump to 2. Between 1 and 2, there are so many things. 1.1, 1.2, 1.3, 1.001, a whole lot of things in between 1 and 2. So continuous variable can assume any value in that manner. So there are variables that are quantitative continuous variables. So let's get that clear. We have quantitative discrete variables and we have quantitative continuous variables. Okay, so continuous variables are normally resulting from measuring something. Okay, let's look at this example. Say the table below provides information of 5 university graduates a year after their graduation. Identify the experimental units and the variables measured. Right, so gender, degree, major, salary, age, GPA. Before, the experimental unit here is the people, the item, the object we are measuring or finding this gender, degree, and stuff on. So this is telling us clearly that the information is on 5 university graduates. So the 5 university graduates are the experimental units. Now let's look at the variables. Now the variables are gender, degree, major, salary, age, and GPA. Which of them are qualitative variables and which of them are quantitative variables? Anybody can speak.
The quantitative are the salary, age, and GPA.
All
Qualitative,
right,
gender, degree, major.
right. And so it is clear, gender, male, female is describing. Degree is also describing your qualification. The major, law, accounting is also describing. But salary, count, age, and GPA are measuring something, right? But age, salary, and then GPA, which of them is a continuous quantitative variable and which of them is a discrete quantitative variable?
Salary and age are discrete variables. GPA is continuous variable.
Okay, I know where you're coming from. Any different idea? Any different idea about salary, age, and GPA? The categories, yes.
The
Indeed.
salary and age are the continuous, whilst the GPA is a discrete.
Okay, so it's the opposite for you. All right, last person to give us middle ground. Anyone to give us a different, or you are either supporting this or supporting that. Okay, so why are you saying salary and age are discrete and GPA it continues? And when you are done, I also ask why the other person turned it around. Yes. So why is salary and age discrete and GPA continues? Is he here or we lost him? Majid, you said the opposite. Why do you think it's the opposite? Why are you saying that salary and age are continuous and GPA is discrete?
Hello, sir.
Yes.
Yes. With I said the salary and age are continuous because um, they don't have like per the explanation you give initially. Per my understanding was that they are not. You don't say 2 points. They are not decimals. Let me put it that way. Whilst the discrete are were decimals, sort of. That was my
So,
understanding.
so you turn the explanation. So discrete do not have decimals. It's continuous that have decimals. Yeah, so that's what I said. So the discretes do not have decimals. They are count 1, 2, 3 like that. But the continuous are the ones that have decimals. They are continuing. So it can carry every decimal in there. Yes. So I know where you're coming from. It's probably because I did not bring any decimal after salary or age. That's why you are saying that they are discrete. But they are not discrete. I mean, salaries can be 100.29 pesos, is that also? So they are continuous because they can assume any value at all. Are you following? GPA is obvious. It has the decimals already. So we can tell that it's a continuous variable, this quantitative variable as well. The same as age. Normally, when we ask you about your age, you only code the year. I'm 25 years, so, right? And you stop there. But it goes beyond the age, which is in years. It can be months, you have weeks, you have days, you have hours, you have minutes. So when you ask you about your age, you are 25 years, 3 months, 2 weeks, 1 day, 12 hours, seconds, and it goes on like that. So you can assume decimals as well. Okay, so age is also a continuous quantitative variable, not a discrete. So there's no discrete in this salary, age, and GPA. They are all continuous. All right. And so the fact that there is no decimal does not change it to be count or countable. Right. So that's the explanation. Okay. Let's now go into the levels of measurement. There are 4 levels of measurement. So any data you have, any data that's been captured or measured, they have measured it on either of these. Either it's a nominal level data, it's an ordinal level data, it's an interval level data, or a ratio level data. And so just like we have when you are in the university level 100, 200, 300, 400, and 400 means that you've gone through level 100, 200, and 300, you are far above the first 3. That's how the levels of measurements also are. So the first one, which we can probably put it as the first level or level 100, right, in terms of levels of measurement, is called the nominal level data. Okay, so nominal level data is a basic kind of measurement that we can have, or level of measurement we can have. Here, the observations can only be counted or classified. So an example, I stand in front of maybe Abeka campus, oh, no, sorry, say main campus, right? Tesano. And then in the morning from 6 a.m. to 6 p.m. And I'm counting cars that passes on that street, right? And what am I doing? I'm counting the cars and classifying them into, say, colors. So I put any car that comes, either it's a red, black, or blue, or green, or yellow, or that is what I'm doing. So what I'm doing is just a nominal level data. I'm just counting and classifying them. Okay. So I'm counting the cars as it comes and classifying them into colors. So I'm putting them into categories. Okay. After which I will say that, oh, from 6 a.m. to 6 p.m., 20 cars passed, and 5 of them were red, 7 of them were blue, 3 of them were that, in that order. So that is what I mean. And that is just counting and classifying them. And it's the lowest level of measurement that we can have. What are the characteristics? The characteristics are that data categories are mutually exclusive. When you say something is mutually exclusive, if I put cars into red, yellow, and green, no car can be red and green. So every category is what? Mutually exclusive. Red cars are in the red category. Blue cars are in the blue category. Green cars are in the green category. And we cannot have one that is here and also here. Okay. So it's mutually exclusive and exhaustive. Exhaustive means that every car that will pass from the 6 a.m. to 6 p.m. should get a category to fit. I can't say that a car passed and I didn't know where to put it. Right. And so the first characteristic is that data categories are mutually exclusive and exhaustive. And then the second one is that data categories are not having any order in them. I cannot rank red higher than green cars and higher than blue cars. So there's no order. Red can be there, blue can be there, green can be there, and they are all the same, no order. All right. So the nominal level data tells you that you can classify, you can count, but there's no order in them. Whatever it is, it just belongs to a category and only that category. And every item you are looking at will have a category they have to belong to. That's all. That is the nominal level data. Then we have the ordinal level data. This is, say, the level 200 of the levels of measurement. So this is higher than the first one. Okay, so the ordinal level data has all the characteristics of the first level of measurement, which is nominal level, and it has something extra that makes it superior to the nominal level data. Okay, so the characteristics are that it uses an ordinal scale of measurement. It means that there is an order in there. So this time around, an example, I'm classifying the cars into categories, but the categories I'm putting it into have order in them. Like say, I want to put cars under superior cars, good cars, average cars, poor cars, inferior cars. Once I'm doing that, what it means is that the superior cars will run on top, followed by the good cars, and followed by the average, the poor, and then the inferior cars. So this one, even though I'm counting and classifying, which is what the nominal level data was doing, I'm also giving some order in the way of categories that I'm forming. Okay, so that is what makes it superior to the first one, which has no order. So it's only the order in here that makes the second level of measurement as higher or sort of on the scale higher than the nominal level data, which was the first one. Level 300 or the third one is also higher than the second and obviously the first one. So it means that it has all the characteristics of the second one, which obviously has all the characteristics of the first one, but it has something else that makes it superior. And the reason why we have ranked it on the higher scale than the ordinal and then the nominal. Okay, so what are the characteristics? Data categories are mutually exclusive and exhaustive. So like the first one, data categories are scaled according to the amount of characteristics they possess. So you can put them in some order, which is the second one. Now, the third characteristic that makes it different is that equal differences in the characteristics are represented by equal differences in the number assigned to the categories. Okay, so in simple terms, let's take measurement of, say, temperature as an example, right? If I tell you that this is 50 degrees, this is 40 degrees,
you
this
were
is
talking
10
about,
degrees.
hello, sir.
Yes.
I think you were talking about the ordinal level data. I don't know why, or you are done with that, you are going to the interval level data.
Yeah, I'm done with the ordinal. I'm on the third one.
Oh, okay.
Yeah. Okay, so with the interval level data, an example is, say, measurement of temperature. Now we can rank it, right? We can rank 50 degrees as very hot. We can rank 30 degrees as hot. We can write 10 degrees, rank 10 degrees as it's okay, right? So we can rank these degrees based on the numbers that is ascribed to them. So 50 degrees is obviously hotter than 30 degrees and then 10 degrees, right? So it can be ranked, and it obviously qualifies for the second level, which was the ordinal. Now, what makes it different and makes it a higher level of data is that the reason why we can tell the difference between 50 degrees and 30 degrees as one being hotter than the other is every degree represents a constant measurement. So 1 degree measures a certain kind of hotness or coldness. 2 degrees, 3 degrees are all understandable. We can understand that because every constant unit of measurement is understandable. All right, so between 10 degrees and 30 degrees, the difference is what? 20 degrees. Between 30 degrees and 50 degrees, the difference is what? 50 degrees. So the change in temperature between 10 and 30 and 30 and 50 are the same, because 1 degree is a constant measurement. You can't say 1 degree between 10 degrees and 30 degrees is different from 1 degree between 30 and 50 degrees. No. 1 degree measures the same constant unit. It has the same constant understanding of representation. So equal difference between two temperatures are the same. So between 10 degrees and 30 degrees, the difference is 20 degrees Celsius. Between 30 degrees and 50 degrees, the difference is 20 degrees Celsius. And these two 20 degrees Celsius are okay. They are all the same because 120 degrees is not different from another 20 degrees. All because a degree measures the same or constant units of measurement. Okay, so that is what makes this interval level data superior to the second and then the first, because it qualifies for the first and the second. It has all the characteristics they have. And the only addition now is that we're able to tell the difference in any interval and understand any interval, right? Because every inch or every number in between the interval assumes a constant unit of measurement. That's why we understand when we say that the interval is between 10 and 15, and then another one between, say, 15 and 20. They all have the same 5 intervals, right? Which is understandable because every one interval measured is the same in any other one interval somewhere else. Okay, so that is the interval level data, which is the third level of measurement, and it's the superior to ordinal and then the nominal level data. Then we have the final or the highest level of measurement, which is called the ratio level data. And the ratio level data has all the characteristics of the interval level data, which comprises the first, the second, and the third levels. It has all of that. But it has one other extra characteristics that makes it superior to the rest, right? It says that the 0 point is meaningful and the ratio between two numbers is also meaningful. What does it mean? The ratio of 1, or when we say ratio between male and female, is 2 to 5. What does it mean? We mean that if you take any number or group, if there are 7 people, you have 2 males and you have what? 5 females. Okay, so that is the ratio. If I tell you the ratio is 0 to 7, it's an understandable. Why? Because it's just telling you that one category is absent and the other category has all the numbers there. Okay, so the 0 point is meaningful. Okay, so any ratio, we understand it because it's also an interval. 1 and 2. Ratio is 2 and 4. It's an interval. It's 2 to 5 or 10 to 20 or whatever it is, an interval, right? But the 0 point is meaningful because it is representing the absence of the characteristic. Okay. And so between two numbers, we also can make sense out of it. All right. And so it has all the characteristics. Data categories are mutually exclusive and exhaustive. They can be ranked. We can talk about equal difference, representing equal difference in the numbers assigned. And the 0.0 reflects the absence of the characteristic. That is what makes it the highest level of measurement. So every data you have will either be any of these, right? Whether it's nominal, ordinal, interval, or it's a ratio. And so that is the levels of measurements that we have. Okay, any questions before we move on to the data collection? All right. So what are the sources of data we normally go for? So we have primary source, we have secondary source. And the primary data source is the one that you, the researcher, gather yourself. Okay, so you design your questionnaire, you take it out there, people will answer the questionnaire for you. It's the first time that that data is being collected by someone, and that's a researcher. So we call that the primary data. So those of you who want to ask your own questions, then get the data, it's a primary data source. So if you are writing up, you tell the story that I'm using a primary data because I'm collecting the data myself, using a questionnaire, blah, blah, blah. That's it. Okay, so there are several ways we collect the data. We'll come to that very soon. And then we have secondary source of data. Data is reproduced from a primary source. That is someone other than the researcher. So it's not you that collected the data. Someone collected the data and you are using the data for your work. So that makes it a secondary source. So get a difference. Now, I know sometimes when students are writing up, they tell you, oh, we use primary and secondary data. And they tell you secondary data from literature review and stuff like that. Literature review is not data. Okay, so data sources, normally, probably if you're using secondary data, maybe you got it from the IMF, World Bank, you got it from the Anasaska Service, you got it from, or if you got it from a journal, maybe someone published his data in the journal and you copied it from there, then fine, that is data you are using. But data in itself that people will write and say, I use primary and secondary data because they review literature. Literature is not data. So don't write, I use primary and secondary data just because you are talking about, you have reviewed some articles in your work. That is not data. If it's data, it is probably coming from, well, it could be a journal that has the data, or it's a book, a newspaper that has the data. It's okay. That one you can say the source is secondary. But if it's not data you gathered from journal, books, newspapers, and those things, then it is not data. Literature review is not data. So you have to be mindful about that. Okay, so let's look through the methods of collecting primary data through a questionnaire. There are several ways. We'll go through them, their do's, their don'ts, their advantages, disadvantages, and stuff like that. And then that will be for the first session. Okay, so let's start. How do we collect data through interviews? Through questionnaires, right? Number one is through personal interviews. Now, personal interviews are the ones that the researcher or whoever the researcher has sent goes to sit with the person that you're supposed to ask the questions and get information and come back home. So these are personal, right? You are there face to face with the person. So it allows for interaction between the interviewer and the interviewee. So I come to you, I sit with you, I talk to you, and I gather my data on my instrument. Okay. it helps to get clarification as and when needed. So sometimes they will not understand the question you're asking. They will ask you, what do you mean by this? Then you get a chance to explain to them further. So that is how personal this one is. You are able to get clarifications. 3, it allows for easy identification of respondents. So if you are there yourself, if someone is not supposed to answer your questionnaire, you are able to tell. It is more personal because you're able to identify this is a student, this is not a student. So I won't allow a person that is not a student to answer the questionnaire. So you're able to tell who your respondents are. And that is one advantage that you can have with personal interviews. Okay. Longer interviews are sometimes tolerated. Why? Because you are there. You are talking, you are chatting, you are smiling, you are sharing jokes, and you are asking your questions. The person will feel okay to still stay and then allow you to complete your questionnaire, even though it's probably long, right? If it were any other way, on the phone or you send it to the person through your mail or whatever it is, these people can decide that this is too big, the questionnaires are too broad, or the questions are too many, I can't answer, and they'll stop. But with personal interviews, they normally allow you to go through and finish, right? And then these days, we use what we call the computer-assisted personal interview. We call that CAPI. So the one that you go with your tablet, your phone, those are called CAPI, computer-assisted personal interview. So data and results, by the time you are done, data is already available. Okay, and these days, that's where we are going. Before, it was paper, paper, paper. I think last week I spoke to you about some of these. But these days, we are moving away from all the paper things, and we are more using the computer-assisted personal interview. Now, usually it may cost more than other forms of interview because you have to be there personally, you have to drive, you have to take transport, you have to pay people to just be there to ask the questions, right? So it usually comes with a higher cost to do these sort of interviews. Now, the second way you can do or collect data through questionnaires is through telephone surveys. Now, this one, mostly common in advanced countries. You call someone, they pick up, you introduce yourself, and you start telling them what you're about to do. And then they say, okay, let's do it. Then you start asking the questions, and it goes on. And here it happens. Those of you who subscribe to even the banks, these days, banks might call you and say that, do you have 1 minute for me to ask you about our product and this is, or can you sort of answer these questions for me in terms of how well we are giving you a good service and stuff like that. DSTV and all these service providers, some of them do normally call through the phone. And this is what we are talking about. So that is a telephone survey, right? And so respondent can be contacted over the phone and it's very fast than the other methods. Other methods, you need to travel to them, like a personal interview. But this one, you just stay in your comfort, the comfort of your office or wherever and call. Okay. You can really have, if you have a directory where you have phone numbers, you can equally shuffle them and randomly call some numbers and then make the questions to them for you to get answers. We can equally use what we call computer-assisted telephone interview, CATI. All right. So the CAPI is the one you would take there, personal interviewing, and the CATI is the telephone interviewing. Right. You can still use your tablet and then fill the answers as you ask the questions to the individuals or to the respondents. And so with these two, data will be available the moment you are done, right? And then it helps to get clarification as and when needed. So if someone does not understand anything, it's just like the personal interview, you can explain to the person and they get it, right? And you move on. What are the disadvantages? We are saying that people are reluctant to answer calls for such purposes. I mean, people these days are not so eager to answer strangers on the phone. So you call them, they might hesitate to answer you, right? They might hesitate. Okay. And then another one is that the working class normally don't have the time to sit on the phone with you for you to ask all your questions. Because maybe if you are calling me and it's my work time, What time will I have for you to answer? I won't do that. You can only get me probably when I'm free at my break time or when I close to work and probably I'm tired or the weekend and stuff. That's when you can get me. But during the working time, it's quite difficult for them to answer these calls. Okay, some might even answer, but they don't have enough time to complete their questionnaire. So that's another disadvantage. And then when you need to show exhibits, tangibles, right? It's difficult because you cannot show them. If they have to read something from a paper or a card, how it is difficult. Personal interviews, you are there with the paper they can read, but telephone interviews, you can't show them any tangible things or objects they can read or say whatever is on it, right? So that's also a challenge that we can have with telephone interviews. Then we have the mail survey, right? So post office. This one usually have the instrument, the manual, user guide, self-addressed envelopes, and then you send it or post it through the mail, right? And so once the people at the receiving end receive the mail, they open it up and then they fill the questionnaire and then put it back into your self-addressed envelope and post it back to you. Okay, these things work a lot in the advanced countries. You are there, you get the mailboxes work. So you get your mail, you open it, it's from one company asking you to fill ABCD. You do that, you send it back to them because they'll put a self-address, something you can just post and put it back in the mailbox, and then they'll come and pick it up, right? And so that is the mail sort of survey. We are saying that it is less costly, and then only kind of survey that if you have names and addresses of the respondents and not their telephone numbers, you can use, right? And then questionnaires can include pictures, things that you can do on the phone with the telephone interview. So you can add exhibits and then you still can mail all of them together, right? It allows for respondents to answer at their leisure time. So when you post it and they receive it, maybe on their weekends when they are free, they can take it and answer and then send it back to you. But the disadvantages are that it might take too long to get the data back. So they might get there to them, but they will take some time before they answer, before they're able to mail it back to you. So that could be a challenge, right? Illiteracy could be a problem. If the person cannot read and write, how would they read and answer your questionnaire for you? And response rates are usually very low because people might not really be willing to respond. If I have to respond, I have to walk all the way to the post office. That can deter me from moving to the post office, and I will not do that, right? And so response rates are usually very low. So if you send 100%, be ready to know that about 70% is what you might receive back. Okay, so those are some of the disadvantages for mail service through the post office. Then we have computer direct interviews. These ones, nobody is there to tell you answer this or that, into you what it is. What happens usually is that you have it like a tablet. You have it like a tablet. It's put at the malls, it's put at the airports, put at certain places, and it's you, whoever that walks to it, you just click and then you start putting in your answers, right? These days, some of the banks to do it. When you are done, they will ask you to scan this and then fill in like a questionnaire about the person or the teller that you visited. Whether the services you got was okay, it wasn't okay, and all of that, right? So computer direct interviews are usually used, especially when some of the things you are going to be asking are quite sensitive, right? If you're asking people about their HIV status like this in a hospital, it would be good to have it as a computer direct interview. So nobody is there. It's just me and the computer. So I'm able to type and show you or answer the questions for you. Even though it's sensitive, I still can give you the answer, right? It eliminates data entry because whilst you are entering the data, it's being captured at the other side. Okay. And it's not biased because it's not like a personal interview where somebody is asking the questions. Sometimes if somebody is asking the questions, they can ask the questions differently, even though they want the same answer. And answers based on the way you ask the questions can vary. But for the computer will ask the question the same way every time, right? So there's likely to be less of a bias in there. When they have skip patterns, it will actually accurately be followed, right? Based on the survey system you have done. And the rate of response is very high. So those of you who have traveled, sometimes in the airport, in the washrooms, before you get out, you see that there's a touchpad there asking you, how did you see the washroom? And it's just somebody sitting behind a computer and observing the responses of people. So if people are saying that the washroom is looking bad, or giving on a scale of 1 to 5, they are giving worse ratings, then it means that somebody will have to be sent right away to the washroom to sort of clean the place because the responses that are coming are not good. So it's a way to actually look at what is happening and even act on certain things. Okay. And so the problem is that interviewers must be literate. Because if you are not literate, you can't go and then be tapping on screens and answering questions. Okay, so our grandmothers who get the opportunity to travel, they will never touch those screens in the airport because they don't know even what it is. They don't want any problems at all. Right? But you who are literate can read and then answer the questions that comes. Okay, and interviewees must also have access to a computer, obviously. If it's a computer direct interview, that computer is the tablet or the whatever is on the wall that you can easily use. And then we have emails. So just like the mails where you use your post office, this one we use the emails, right? So you have the email addresses of people, you have the questionnaires, you can add videos, you can add photos, whatever exhibit you have, and push it. And then once people receive it, they open it up and then fill the questionnaire for you and send it back, right? So the rate of response is usually very high because you can gather thousands of responses within a second. Within a day or two, you get a lot of responses. And there's practically no cost once you set it up, okay? You attach pictures, videos, sound files, and all of that. That can be done. The problem now is you need to obtain a list of email addresses. And you know how email addresses are. The hyphens, the dots, the capital letters. If you are typing it and it's wrong, you get a lot of failure in terms of delivery, right? So you have to be cautious as to how you do it. Okay. And some people can respond multiple times because it's an email. Once they open, they click and start filling it, they can send it again multiple times, and that could be a problem. Or they can pass to friends or secretaries or whatever who is free to answer it for you. So they might not really be representative of who you want to answer the questionnaire for you. Okay. And then sometimes you can't use findings to generalize for the population, especially if there's no randomness in the emails that you used. If it is email to my colleagues at work, and the work is not about my colleagues, right? Then generalization becomes a problem. Okay? It's just like you sending the thing on WhatsApp, okay, to people, or Facebook to people, and they click and then answer. They are not random enough. You cannot generalize for the population. Okay, so email surveys cannot automatically skip some of the questions, you know, and you have to use other automatic techniques that will use the surveys. So there are some advantages and disadvantages for each one of the different ways that we can gather data. Then we have the internet or the web page, the intranet service. So this one, normally people pay the hosts, and then whilst you are on the internet, you see that something will pop up. And once it pops up, you click, and then you have to answer the question probably before it allows you to move on to whatever you were doing. And so in search instances, you are able to get a lot of data because if people are really browsing, they are doing their stuff, and that one comes. And they can't easily close unless they finish answering that question. Then everybody that is browsing on that site becomes a potential respondent to your survey. And you can get a lot of people answering for you because once they are keen on browsing that particular page, they will fill the questionnaire before they move on, right? And so it works and depends on, it could be a banking site. You want to do a transaction, but before you do the transaction, something pops up, and then you have to answer it before you move on to do what you have to. So long as the person wants to do the transaction, they will do that sort of fill in that survey for you before they move on, right? So they are fast, and if posted on a popular website, you can gather several thousands of responses within a few hours. Okay, and there's practically no cost. So long as you set it up, pay the host, everything is working. You can show pictures, videos, sound files, and web-based questionnaires can be as complex as you want because you can put in all the logic, the algorithm, whatever you need, randomness. So you can do randomization with it. So it's not everybody that will get to answer the questionnaire. You can randomize it and pops on people's screens randomly. Okay. You can use different formatting tools, font colors, which probably are not possible with other ways or other forms of gathering data. Accurate answers to sensitive questions can, just like the computer direct interviews, this can also be because you are sitting in front of your computer and it pops up. Nobody is there. You can feel any sensitive question, no matter what it is, right? Because nobody is watching you, nobody is asking you the question directly, so on. You can help people give longer answers to open-ended questions because it's at probably a comfort of their homes. They can easily do a lot of things for you. All right. Now, the problems are that the current use of the internet is not universal. It's not everywhere people get internet. So if you have it on a website and people are not able to browse, so you might be doing this in the urban areas alone or places where there's internet, but places where it matters most, you might not get them to answer because there's no internet. People can easily quit in the middle of the questionnaire, and sometimes you have no control who is answering the questionnaire. It could be a site where adults will have to be, but you see children also going there, and it pops up and they click, 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 click. You don't know what is happening. You have no control over the number of times one can answer a web page questionnaire. But these days, I think you can. Technology has advanced where IP addresses and stuff like that. So we can know and restrict. Once it pops on this computer, it won't pop on it again. So you can restrict who or the number of times that one will answer particular web page questionnaire. All right. So each and every one of these that we use to collect data on the using questionnaires, right, have their positives and then their negatives. It is up to you, the researcher, to sort of act or choose which one will maximize what you really want to achieve. Right? So the one that will give you the highest advantages opposed to the one that will give you the lowest. So you choose the one that works for you. And that is going to be helpful. Right. All right. Any questions on the levels of measurements and then the ways we gather information through the questionnaire? All right. I believe it's a straightforward thing. That is here. Okay. So I will start with the other slide that we were supposed to use in the other session. Then let's see how we go. If we close early, that's it. And we can take the other time to do our own thing. Good. Okay, so let's continue with data analysis in quantitative research. So as I said, the focus will be a bit skewed towards quantitative research because of course, economics, whatever the topic you have, will have to be quantitative in nature, right? So let's focus more on how to do your analysis in quantitative research, right? So now you've been able to design your questionnaire, you know the levels of measurement, each variable that you have. So how do you go ahead with the analysis that you have to do? Okay, but before that, you want to look at the overview of data analysis in quantitative research. I've spoken about some of them. I'm just going to walk quickly through the process, right? So when we talk about quantitative research, it involves a systematic empirical investigation of some observable phenomenon through statistical, mathematical, or computational techniques. So you have data, and you're going to use statistical ways or mathematical ways or computational ways to sort of analyze it, right? You are investigating something and through empirical evidence, okay? So the overview here starts first with the data collection, as we have just spoken about. So you've collected your data quantitatively, and you've done that through surveys or questionnaires, through an experiment, through observation, through secondary data, that is data, the databases from other places. That is your data collection. So those of you who use secondary data, by now, you should be thinking of where am I getting the data from, right? So for primary data, you know you're going to collect the data yourself, design your questionnaire, and it goes on. But for secondary data, you are thinking of, okay, will I be using data from World Bank, IMF? Or will I be using data from African Development Bank? Will I use the data from Bank of Ghana or wherever, right? So we need to be thinking about that's the data collection. After that, you prepare the data. So if the data is primary, okay, a lot of work has to go in because data has to be coded, it has to be analyzed in such a way that, or clean, first of all, clean. And we say cleaning, we are talking about any sort of errors and inconsistencies that might happen in your data collection. Okay, skip pattern. So you ask the question, how old are you? And the person says 18. And the next question says that if you are 18 and above, you have to answer this. So all those that are 18 and above goes to answer it. But you realize that people that were even 17, 16 were answering it. Now that's a problem. It's an error. You need to correct all of these before you can analyze your data and bring out charts and tables and any other analysis, right? And so data cleaning is a very important part of data preparation. Even if you go and take secondary data, sometimes that data is also not clean the way you have to or you want to. So you might go in there and look through for consistencies, look through for errors, and clean them. Make sure that the data is now okay to be used for analysis. Okay, sometimes you have very huge outliers, right? So income, how much you earn in a year or in a month. Somebody is saying to think through. How maybe a mistake? The person was typing 5,000 and added one more zero. So you have to watch all of these and correct sort of right before you start using the data. Because if there are huge outliers and you now want to do mean of on an average of that particular income, you realize that that 50,000 is going to make your mean so huge. Meanwhile, it is only one variable, one person that gave that 50,000. A majority of you people or your respondents are having 2,000, 3,000, 4,000 as their income per month. So if you find the average, including that 50,000, the average might hit you to 250,000 or something. But is that representative? Is that what is really the case? No. So if you don't clean the data, some of these things might be the problem. somebody will question you, are you sure the average age of your respondent is 250,000? But it's because we have one big outlier somewhere that is creating that problem. Okay. So data cleaning, data coding, data entry, and all, and those are considered under data preparation. And after data preparation, you can either decide to do a descriptive statistics or inferential statistics as part of your analysis, right? So you are doing descriptive statistics, you are doing measures of central tendency, mean, median, mode, you are doing measures of dispersion, range, variance, standard deviations, frequency distributions, you are drawing charts, pie chart, histogram, and so on. All of these are describing your data. That could be your analysis. And as I said, it could be a descriptive research design that you chose to use. And you'll be fine by describing whatever is there. But this is still what? Quantitative. Because if you describe the average and you put it in a table, chart, or whatever it is, the mean, median, and mode, it's descriptive statistics. It is describing the data, how the average is, the mean, median is, and the mode is. Or you can do inferential statistics. This is where you put more rigor, right? So you draw conclusions from a sample to a population. So you can do hypothesis testing, confidence intervals, regression analysis, analysis of variance, and so on and so forth. All of these are inferential statistics because you are using a sample to generalize for the population. Okay, those are some of the techniques that you can do. After you have described or you've done inferential, you can interpret your data. Okay, so what result did you get? You have to contextualize your findings, all right? So relating your results to research questions and then the hypothesis that you sought to find. So if you ask yourself to answer these objectives, how does your interpretation sort of come to answer your research objectives? Do they answer it or they don't answer it? All right. You look at the limitations. You acknowledge the potential biases in your analysis, the limitations from the data that you gathered and the analysis you're doing. You draw conclusions. You make informed conclusions about based on the analysis, right? And then how do you report the results? Research papers, presentations, and you can do that through charts, graphs, tables, and so on and so forth. So the overview of research in terms of quantitative analysis, we'll have to go through these stages that I have spoken to you about, right? Data gathering, cleaning or preparing the data, your analysis itself, interpretation, conclusions, and so on. Okay, what are the importance of data analysis? I mean, why do we analyze data in the first place? So one, data analysis is very important in research for several reasons. One, for reliability. So if you do a proper data analysis, right, it ensures that the data becomes valid and it's reliable for research of the research findings. So somebody can say that, oh, based on ABC that you did, I really trust the results you got. And so it's reliable or it's valid. Okay, it helps to confirm that the data collected was accurate, right? And reflects the true meaning of whatever is in existence. And again, somebody can also replicate it. Somebody can do the same thing and you are certain that the same results are what the people are going to get. Okay, so it has to be reliable, it has to be valid. It identifies the patterns and the trends. So anytime you're analyzing data, those are the things you're looking at, patterns, trends, and then this can lead to new insights and then understanding in the field of study that you are looking at. Okay, it can help you make informed decisions. Once you analyze data, now whatever conclusions you are drawing can be used to make informed decisions. Okay, and based on that, you can recommend as well. Okay, so conclusions come, you recommend based on your conclusions, and it's crucial for using this in applied research, right? So you apply this research findings in a real world context, and then you make policies, healthcare, business strategies, and so on. All of these based on data helps you make informed decisions. When you're analyzing the data, it helps you reduce error. Equally helps you detect errors. So if I tap and I analyze the data and I realize that the average for income in a month is 300,000, I mean, it will raise a red flag for me, or it will hint me that no, this cannot be right. So once you are analyzing, you're able to detect the errors. You're able to correct these errors and reduce as much as possible the errors that exist in the data. Okay. We can use it to test hypotheses. So through some statistical analysis, the tests of hypothesis can be done and determine the likelihood that the findings are actually due to chance. All right. And so mostly we are able to generalize the results if you're able to do a proper hypothesis testing. Now, hypothesis testing is big. With some of the analysis we do, they are all hypothesis testing. I can ask or say, I'll make the claim that female students in this class will do better, or females normally do better in this class than maybe males, or the opposite. Now, this is a claim I've made. I need to collect data on your results, on past students, their results, and now find out really if all students of this course, the females are normally doing better than the males or otherwise. So I either confirm my claim or reject my claim. That's hypothesis testing. Okay. The average income of this class is 1,005. I collect data on your incomes. I test and find out. Yes, indeed, it's more than 1,005. It's always the same as 1,005. I either reject the claim or accept the claim. That is hypothesis testing. That can be done through data analysis. Okay. Resource optimization. Efficient data analysis can also save you time. Saves you a lot of resource, and it helps you go straight to the point. You analyze the most relevant data and reduce the need for redundant and unnecessary data collection. If you know your objectives and you go straightly by objectives and ask the relevant questions, you really save a lot of time without wasting people's time and your time. Okay, it helps in transparency and replicability. So once you do how you did it, and they can equally decide that let me replicate it. And I'm sure some of you, your research topics are topics that you've seen in other places, not Ghana, but you feel that I can do this for Ghana. It's good to replicate. There's no problem with that. Okay, it can be a gap that you see in the literature that, oh, this work has been done only in developed countries, but I think I can do it in developing countries as well. And that's a gap right there. And you can use that and follow through, and your research will add some insight on the African context to the literature that is available. Okay. Okay, so let's look again on data analysis and how we do these sort of interpretations, right? So once you are doing the analysis, your whole point is to be able to interpret. After you have examined, you've seen the patterns in the relationship, the trend, the data. And it depends on whether you are doing a quantitative analysis or qualitative analysis. Right? So if it's a quantitative analysis, as we said, you can do descriptive statistics, right? You summarize the data, like the mean, median, mode, and stuff like that. And then if it's inferential, you test the hypothesis, you draw conclusions. You can use things like the t-test, the ANOVA, and the regression analysis to do that. Okay, so that is quantitative. Qualitatively, you have to code it, you have to categorize this, you have to identify the themes in there, the patterns from interviews, focus group, and open-ended questionnaires, and so on. All right, so qualitative analysis will tell you the kind of analysis that you can do. You can do the narrative analysis where you understand stories and experiences shared by participants, right? You can do observational studies where you go be with the people, observe and document, right? So that's your analysis. It can be content analysis, thematic analysis, whatever you want to do. And it depends on the fact that it's either quantitative or qualitative to know what exactly you need to do. Then we have the mixed methods. You're combining the quantitative and the qualitative approach to do the analysis. Okay. And so what the numbers will give you in terms of quantitative, you use the qualitative to support it. And that becomes a mixed method, which can also be equally used. Okay. And when you are interpreting, it involves explaining the results of the analysis, and then you are linking them to your research objectives. Don't get what your research objectives were about. Okay, so you understand the trends, you know the patterns, the insights, you contextualize the findings, right? Your results has to match up with your research questions or hypothesis, and then you draw your conclusions, and then recommendations follow. So you formulate clear, evidence-based conclusions. I don't know if I've said it here before, that whenever you are drawing your recommendations, it has to come from your conclusions. Don't go out of the research you have done and go recommending on things you did not do. Okay, only make sure that you are giving recommendations from your conclusions that you have had on the work that you have done. That is the bottom line. Okay. Any questions before we look at the data analysis itself and take them one after the other, from descriptive to inferential and all the rest? Any questions? Yes, Charles.
Good afternoon, sir, and thank you for the opportunity. When you started this topic, you stated that because of the economics course, that most of the economic researches are quantitative, are supposed to be quantitative in nature. So if I decide to use primary data, to which extent am I supposed to rely on the primary data to make it more quantitative for it to be accepted as an economic research?
Yeah, so when we say primary data, secondary data, quantitative, qualitative, we're just talking about the variables in there. Those are what makes it quantitative data or qualitative data, right? And so if it is data that you are gathering yourself, the questions you are supposed to ask in your questionnaire should be quantitative questions in nature. You understand? So there has to be variables that are measurable. The things you are asking questions on should be measurable. The moment it's measurable, it turns quantitative, because I can find the mean of it, the median, the mode, and all of those. Then it means that it's quantitative. You understand? So every variable or every question that you are putting out there, especially in terms of your objectives, what you'll be measuring in your objectives, those variables in there has to be quantitative. That's what makes it quantitative. It's no other whether it's primary data or secondary data. No, it's a measurement that will have to come in there. Okay. So if I'm interested in looking at let's say consumption, okay, in households, right? And I want to find out the effect of maybe income increments or higher income on consumption patterns in Ghana. Now, consumption has to be measured. Income that is increasing has to be measured. So how am I measuring my income? I'm asking the questions. What is your monthly income? I'm not going to do it in such a way that whatever way I'm measuring the income is sort of qualitative, right? It has to be, I leave a dash and say, what is your income? 5,000, 10,000, 7,000, 2,500. That makes it quantitative variable, and I can measure it. I can find the average, the median, the mode, all of that on that particular variable. If I go to the consumption, I should be able to also measure the consumption. You understand? So that is what makes it quantitative. And the analysis that you are going to do on it, because they are numbers, you can do statistical analysis on them. Whether it's the measurement of central tendency, whether it's measures of variability, whether it's inferential, where you are doing hypothesis testing or you are doing regression, correlations, and stuff like that. They are all quantitative ways of handling your data. So your questionnaire should have questions that are quantitative. It doesn't mean you should not have questions that are qualitative, like gender. Gender can be in there, all right? But we can, if marital status can be in there, they are qualitative variables, but we can have a way and use that in a quantitative analysis. You understand? Yes. We can even have Likert scale in there, in your opinion, and we can form indexes out of those Likert scale, and we can really use that to do our analysis. So primary data is not necessarily, you can do quantitative analysis with primary data. Depends on the questions you're asking. Is that okay?
Yes, sir.
Any other? Okay, so let's look at what kind of analysis you can do quantitatively. And one is descriptive statistics. So we can choose that our research design is descriptive in nature. And by descriptive, the only way that can make it quantitative, if we are measuring it in the measures of central tendency. So you have the variables in there. You can measure the mean, the median, which is the middle value, the mode, which is the most frequent value, and so on and so forth. So it can be a variable like, say, income or exam scores. And out of the exam scores, I'm looking at these measures. And that will change it automatically to quantitative analysis, because even though you are describing what it is, you are describing the middle of the data, which is the central tendency, it is still quantitative. 2, you can do measures of variability. I want to find the difference between the highest value and the lowest value. That is called the range. I want to find the standard deviation, the average distance away from the mean. That is descriptive. I can want to find the variance, right? That's the square of the standard deviation. Example, calculating the range and standard deviation of the height in a class. I can do that, and that is descriptive in nature. That's quantitative analysis. Okay, and so we can do that, and that descriptive. So descriptive can also be done using charts. We can use pie chart, we can use bar graphs, we can use histograms and stuff like that to line graph, dots, the scattered diagrams or scatter plots and so on. You can use all of that to be describing how the data looks like. And that is quantitative research. But the approach, the design here is what? Descriptive. We can have it in a table form where we have the mean, median, and so on, standard deviations, as we see here. We can have all of that, and that can be descriptive statistics without any doubt at all. Okay, we can do them through tables, right? And most of us do that. So we have a table that sort of talks about gender versus marital status. So how many males are married, how many females are married, and so on. That is descriptive statistics, right? We are describing the data, the numbers that we see. An example, looking at the classes and how many live on campus or off campus, right? So it's a freshman, or that's somebody who is in the first year, a second year, which is a sophomore, a junior, or a senior, right? In the US, that's how they put it. Okay, so you are a first year freshman, second year sophomore, and it goes on like that. And so this table like this is a descriptive statistics, right? We are representing the data in a descriptive form. So when I'm writing this up, I'm just saying that, 100 people out of 137 are freshmen, and they live on campus, relative to 37 that are freshmen that are living out of campus or off campus. and you go ahead and describe it. That is description. Okay. It can be in this table form, right? The observation, the mean, the standard deviation, minimum and maximum of these variables. We can describe this as well. And this is also a descriptive statistics. All right, so we can do a descriptive design and do justice to the research topic. If the objectives are in a description form, we can do that. Okay. Then we can do this same analysis in the form of what? Inferential statistics. So inferential statistics is that you're using a sample to generalize for the whole population. In that instance, we can do it through hypothesis testing. So I make a statement I call the null hypothesis, and the opposite is the alternative hypothesis. So if I make the statement that the average income in this class is 1,000 cedis, right? The opposing or alternative hypothesis would be that the average income in this class is not 1,000 cedis. And it's up to me, the researcher, to gather data and really say that I'm going to confirm whether the statement is the average is 1,000 cedis, or reject the claim that it's 1,000 cedis and go for the claim that the average is not 1,000 cedis. So that's hypothesis testing. Okay. So we can do hypothesis testing as an inferential statistics in a quantitative research or in quantitative data analysis. Okay. We can do t-tests. T-tests are other forms of quantitative analysis where we are testing the hypothesis that one group is the same as the other, or the one group is different from the other. Okay, so I'm comparing the means of two independent groups, let's say between males and females. I collected data on your scores in exams, and I want to find out the average performance of males is the same as the average performance of females, or the average performance of males is not the same as the average performance of the other group. Okay, so it's a test on itself. It's also a hypothesis testing that there's a difference between the two groups or there's no difference between the two groups. Okay, we can also have what we call a paired t-test. This one compares the means of the same group at different times. So I collect data on only males, first semester and second semester. So now what I'm doing is that I'm going to compare the same group, which is males, between the first semester exams and the second semester exams. So it's the same group, but it's at different times. That is also called the paired t-test. The independent t-test is different because we are comparing among two different groups, like males and females. Okay, or like morning students and evening students, or master students who are doing economics and master students who are doing marketing. These are two independent groups that I'm trying to compare. And that is what the paired t-test is about. Okay, good. And then we have chi-square test. Chi-square test is also a test that tests the relationship between categorical variables. Now, the t-test I'm looking at, the hypothesis testing that I'm talking about, normally we test these on quantitative variables, whether discrete, whether discrete or whether it's continuous, right? We test it on them. But chi-square tests normally will test the association between categorical variables. What do you mean by categorical variables? Like male and female, right? Like marital status, married, single, divorced, separated, and so on. These are categories. They are categorical variables. They are qualitative variables. And so we can equally do another test on these, and then those can also represent quantitative analysis, right? And so chi-square tests will make categorical variables more looking like a statistical analysis, okay? And so we can test the chi-square test to examine the association between gender and course preference. So we can find out, is there a relationship between the gender you are, male or female, and choosing a particular course at the master's level? Okay, so the courses could be HR, it could be management, it could be economics, and I find males and females. So I find out, is there a relationship between being male and the choosing of a particular course, or being female and the choice of a particular course? And being male or female is categorical, right? And also the number of course or the type of course I'm doing is also categorical. So if you have two categorical variables, we can equally do statistical analysis on them. Okay, and we can use the chi-square test to do that. We don't use t-tests on categorical variables. T-tests are only for continuous variables, or the incomes and age and performance and scores of something or heights of something or those sort of things. Right? So let's bear that in mind. So this is an example of a t-test, and this is coming from SPSS, right? So those of you who know SPSS or have used it before, here, what is being tested is that we want to find out if there's a difference in the scores for sugar, right? So the mean was 12.2, standard deviation was 1.3, and no sugar, right? So between sugar and no sugar, these are what we are trying to test. Are the means the same or they are different? So the means for sugar was 4.2, the mean for no sugar was 2.2. Okay, and so we want to test. So we use a t-test because this is a t-test of different groups. It's not a pair t-test. This one is for different groups. So this is the t-test we are talking about, the independent t-test, right? So you see on top here as independent sample t-test, telling you that you're talking about two different groups. We want to find out if they are having the same mean or not. Okay, so this table, I'll just go through it and then see how best we can follow. Because these are some of the things that you can do in your quantitative analysis, right? You can do t-tests to find out if there are differences between groups or not. Okay, so let's look at first, this is the output that will come from testing using a t-test for two groups. So here, the two groups are sugar and no sugar, right? And the mean for the sugar is 4.2, and the mean for the no sugar is 2.2. Now on the surface, with your eyes, if we ask you, is there a difference between 4.2 and 2.2? Yes, obviously, there's a gap, there's a difference. We can say that. But the point is that we need to test it statistically to tell us, yes, indeed, there's a statistical difference between sugar and no sugar, or between males and females in terms of performance, in terms of their GPA or their class score or whatever it is, right? And so normally to find out some of these, we have things we look out for on the table, right? And so we have, first of all, this column, we call it the T statistic, right? And then second column, we call that the degrees of freedom. And then we have the third column, we call it the significance level. Okay, please, let's pay attention because in all the analysis, quantitative analysis you do, these are what you'll be looking out for. And the best way to help you understand and interpret your data is what I'm trying to start off here, right? And so we have something called the p-values. They are the values we look on and decide whether whatever test we are doing is statistically significant or is statistically not significant. Okay, good. Now, if we take the T statistic here, 2.887, then this also gives us 2.887. Now, the rule of thumb for every T statistic is that if the T tests, the T statistic, right? If the T statistic is greater than 2, we say that reject the null hypothesis. Right? The null hypothesis is called HO. Reject the null hypothesis. If the t statistic is less than 2, then we do the opposite. We accept the hypothesis HO. That's a null hypothesis. Now, null hypothesis is always the statement that you make as a researcher. Okay, that is your claim. All right, so in the t-test, the claim that you always will make is that for HO, right, the null hypothesis, you claim that there is no difference between the two groups. I believe this is the things you have to write in your book, right? So it tells you that there is no difference between the groups that you are testing. And then your H1, which we call the alternative hypothesis, is the opposite of the HO. So we say that there is or there are differences between the groups. Okay, so every hypothesis is tested on two statements. The first we call the null hypothesis, the second we call the alternative hypothesis. The null hypothesis in this instance is that you are testing the difference between two groups in terms of particular variable. Now, the null hypothesis is saying that there's no difference. The alternative is saying that there is a difference. Now, your duty is to gather data, collect the data, which we have done, and then you go through the system. The system has already given us the results based on the data that was available. And it is saying that we either choose whether to say HO is correct, that there's no difference between the two groups, or H1 is rather the correct one. It means that there's a difference between the two groups. Okay. Now we have something called the level of significance. We normally represent it with alpha. Okay, we can have alpha to be 1%, 5%, or 10%. Remember from last week, when we were doing the sampling, and I went to the internet and we were doing the sample size, you realize that we had 95% confidence level, we have 99, we had 90, and the rest, right? And then those are what is bringing about this level of significance. So if I say that my level of significance is 1%, what it means is that I am 99% confident. Okay. So I'm 99% confident. So my confidence level is equal to 99%. If I choose 5% as my level of significance, then it means that I'm only 95% confident. Okay. The same way, if I choose 10% as my level of significance, it means that I am 90% confident. Okay, that's my confidence level. So significance level is just saying that if I'm 90% sure, I am 10% not sure. If I'm 99% sure, I am 1% not sure. If I'm 95% sure, I am 5% not sure. And so those level of significance help us to actually get to either accept the HO or reject the HO. Okay, and go for the H1. At any point in time, one of the statements is what I'll have to conclude on when I'm doing hypothesis testing. It's either I say I'm going for HO or I'm rejecting HO and going for H1. Okay, that is how the hypothesis is done. Okay. Now, how do we use these significance levels here to determine whether we reject the HO or we accept the HO? Or before that, let me just use my rule of thumb already. I've said that the rule of thumb for t-test is that if it is greater than 2, right, we reject the HO. So let's look at our t statistic here. This t statistic from our table is giving us 2.89, right? 2.89. So what do we do? Based on our rule of thumb that we have specified here, if it is greater than 2, reject
Reject all hypothesis.
right? Yes. So this one is saying that it's 2.89. So it's greater than 2, isn't it?
Yes, sir.
Yeah. So we reject the HO. What is going to happen is that rejecting the HO in this instance is going to say that I have to reject this statement, which is saying there is no difference between sugar and no sugar. Right. So if I'm rejecting the HO, then what am I going for? I'm going for the H1, which is the alternative statement or the alternative claim that I also made. So the main claim HO has been rejected. It means that I cannot go any further than to say that H1 is a correct claim. And what is H1 saying? H1 is saying that there's a difference between the two groups, which in this case, sugar and no sugar. So the 4.2 and the 2.2 that I'm seeing as the mean for the two groups are different. That is what hypothesis testing is about. You make the claim, you gather evidence through data, right? And then you subject it through statistical rigor. And then whatever the outcome is, you make the statement as to whether HO is being accepted or HO is being rejected. If you reject HO, then you go ahead and accept H1. And then you conclude on that. And that is your conclusion that you are going to use at the end of the day in your work. Okay, so this is the rule of thumb explanation, which is clear. Let's move away from the rule of thumb and now go to the p-value that we have here, which we can also look on and make a decision. Okay, and most importantly, the p-values are what we critically will look at to make a decision whether to reject the HO or accept the HO. So how do we do this? Let's pay attention. We are saying that our level of significance, which is our alpha, is either 1%, 5%, or 10%, right? Let's put it into decimals. 1% will give us what? 0.01. Is that not it? That is
Yes.
1%. What about 5%? 5% will give us
0.05.
0.05, right? Okay, what about 10%? 10%, 0. So this is our level of significance. So alpha can be 0.01, alpha can be 0.05, and alpha can be 0.1, which is 10%. Yeah. So when you are doing these things, the best is the 1%, right? Just from last week, you remember when we were selecting our sample, whenever we chose 99%, you realize that the sample size became very big. When you reduce it to 95%, the sample size becomes a bit smaller. When you reduce it to 90%, you really have a very small sample size. And I told you that for you to be believable, for somebody to believe your work, it's always good to have a very large sample size, and you're supposed to have margin of errors that are very small. You understand? The better somebody will believe the work that you have done or the results that you have. So whenever your results come out, you first of all look at the level of significance of 1% before you go to 5% and finally 10%. 10% is when you really don't have much to say, then you will go with 10%. But if your results is all significant at 1%, then the results are very strong. Okay, so we always compare 1% before 5% before we get to 10%. So let's start comparing. Now we compare what we are calling the p-values. or in some instances, in some books, you will see significance, right? Significance, you see this, SIG, that's the significance level. In some instances, you see that they have written P value in that column. That is what we call that probability values, right? And what's the probability value here? This is 0.020. If you send it to percent, this is 2%. Yes, 2%. If you take the second one, it's 0.24. So significance level to the probability levels or the p-values that you see here. And based on that, we take or we make a conclusion. Okay. And so anytime that our significance level is less than, anytime that our p-values here, right, as we see here, is lower than the significance level, which is the alpha, we reject the null hypothesis. Okay, so that is the rule. Anytime that the ones you're seeing under the significance here, anytime the values you see here are lower than our alpha levels we have put here, we reject the null hypothesis. Okay, so if the p-value is less than our alpha, the conclusion is that reject the H0. Okay, that's the rule. So let's start looking at the values and see what the decision will be if you want to reject a null hypothesis or not. Okay, so let's take this first one here, 0.02. If you convert to percent, that's 2%, isn't it? Now, if you compare the 2% with the first alpha, which is 1%, what will be our conclusion? Right? So this is 2%. Right? It's 2%. If you compare the 2% with 1%, what will be our conclusion? Based on what the condition I've written here, if the p-value
We reject
is
the null hypothesis.
Say it again.
We reject the null hypothesis.
Are you sure? The p-value is 2%, 1%. What will be?
We are
We accept.
we said because
Yes.
the p-value is greater than the alpha.
Exactly. So we will go and accept the HO, right? If we consider the alpha to be 1%, then we have to go and accept what? The HO. You get it? Good. Now let's look at if we move away from 1% and go to 5%, what will be our decision?
We reject.
Good. So at 5% level of significance, our p-value is lower than the 5%, isn't it? So it clearly tells us to reject the null hypothesis and go for said. The best is 1%. If you are not able to satisfy your objective, which is, or you are not able to reject the null hypothesis under that 1%, you move on to 5%. Okay. And here we get to see that under 5% level of significance, we can reject the null hypothesis, which is saying that there is no difference between the two groups. High standard. It tells us that indeed there's no difference between these two groups. That's why we are accepting the null hypothesis. But if we reduce the standard a bit and go to 5%, that means that we are allowing more room for errors. So at 5%, it is giving us the opportunity to reject the null hypothesis. So if 5% have rejected it, obviously 10% will also reject it, right? And we don't go beyond 10%. Now, statistically, the
Run away. Yes, I didn't see the person. You want to find the person? Yes, please. Healing and
so statistically, we consider these three levels of significance, either 1%, 5%, or 10%. Now, the normally accepted one is 5%. Can be insignificant under 1%. So it is okay to interpret your results when it's under 5% level of significance. You have no problem. Make conclusions about your 5%, you are fine. It's okay. It will be accepted generally, right? But if it is about 10%, the people will look at you one or two, right? They will not be so convinced because you have given yourself more room for errors. Even though in the worst case, when you are not getting significance under 1%, 5%, you are forced to accept or use 1% so that your objectives most likely to be agreed or satisfied. Maybe you have made a claim that there's a difference between the two groups, right? That's what you want to see. But if you're looking at 1% level of significance, it's saying there's no difference. You might go to 5%. It's still saying that, yes, it's saying that there's a difference. You stick like that. You write your write-up because that's a narrow escape, right? In your research, you take it like that. But the standard, as I've said, is that you want to see it significant under 5%. Everybody will believe it is okay, 5%. But it is good or it is the best if you see it as significant under 1%. That is the ultimate that you can get in any research, under 1%. So any book, any paper you look at, some of them, you see that in the results, they will put stars on top of it, right? And normally, if you see 3 stars on top of a variable, it is telling you that it is significant under 1%, which is very good. If you see 2 stars, it is telling you that it is significant under 5%, right? And if you see just 1 star on a variable, it is telling you that that variable is statistically significant under 10%. Okay, so 3 stars is always better than 2 stars, and 2 stars are always better than 1 star. But we don't have 0 stars. So if you see any variable with no stars on it, it tells you that it goes beyond 10% level of significance. And statistically, it is not significant. So you leave it at that. You can't go ahead and interpret that variable and make conclusions on that variable because there's no significance statistically on that variable. All right. I hope I'm making sense. But this is your bottom line for anybody that wants to do quantitative work. This is how you always interpret your coefficients or your results statistically. Because all the statistical analysis you are going to do, most of them are hypotheses. And you always have a null hypothesis and an alternative hypothesis. And you are either rejecting the null hypothesis or accepting the alternative hypothesis. Those are the things that will happen in every scenario, right? We will have some regression results.
Hello, Doc.
Yes.
Please, can you go over the last part again, the p-value and the alpha?
Which one? The alpha?
Yeah, the
and
alpha
the
and the...
p-values?
Yes, please.
Yeah, so in every statistics, in every hypothesis testing you are going to do, you are going to have columns that are indicating what we call p-values, right? Probability values represented by p, right? And then you are also going to know, this one has to be at the back of your mind, that we are always testing the hypothesis under 1%, 5%, or 10%. That is the rules. So this one, you need to write it somewhere as the rule. 5%, 1%, or 10%. you are always going to compare your 1, 5, and 10% to the probability value that the software has given you in terms of whatever you see on the table. Now, the rule is that if the probability value is less than the alpha that you are interested in, you reject the null hypothesis, which tells you that anytime you are testing a hypothesis, you need to know your null hypothesis and the alternative hypothesis. The null hypothesis is always the claim that you, the researcher, has made. Okay, so I'm making the claim that there is no difference between males and females in this class. That's what we always expect. We don't expect males to do better than females, right? So the expectation is that there's no difference between males and females in this class. Now I collect data on your results. Now I found the mean performance of males, mean performance of females. Now I test to find out, is there a difference between these two groups? Now the table has given me a p-value. That p-value has to be compared with my statistical, my significance level, 1%, 5%, or 10%. The best is what? 1%, right? Followed by 5% and followed by 10%. Okay, so we are telling the story of, am I going to take the null hypothesis or am I going to take the alternative hypothesis? Okay, I'm only going to be able to know this if I compare my level of significance. That is the room that I want to give for errors. 1%, 5%, or 10%. I'm comparing that with the p-value that the table has given me. Now, the rule is that if the p-value is less than 1%, 5%, or 10%, reject the null hypothesis. Right? Anything more than 10%, we don't consider, right? We tell ourselves that we cannot reject the null hypothesis. So you can first compare with 1%, right? Or just before, once you turn your p-value into a percent, if it is 0.24 or 0.024, if you convert this straight away is 2.4. So you don't waste your time 2.4%, 2.4%. You don't go and waste your time with 1%. You already know it's greater than 1%. Right? But it is less than 5%. So statistically, it's less than 5%. So it tells you that you can reject the null hypothesis under 5%. If you observe this and it was 0.06, right? If that was what the p-value was, 0.06. Now, if you convert this 0.06, it's straight away 6%. 6% is more than 1%, it's more than 5%, but it is less than 10%. So obviously, you are only able to reject the null hypothesis under 10%. So you just have to convert to percent and compare to 1, 5, or 10. So long as it's less than 10%, you are going to reject the null hypothesis. That is the
Thank
rule
you, Doc.
But sir, I have a
you always abide by. And this has to get in.
sir, sir, I have a question.
Yeah, go ahead.
Yes, sir. So, for example, the example you just gave of maybe a p-value of 0.06, which would be higher than
Yeah.
1% and 5%.
Yes.
Does it also mean that you can accept the hypothesis under 1% and 5%? That's my question.
You are not accepting when 10% is rejecting it. That's why I
Oh,
said in
okay.
statistics, these are the 3 levels we look at. So you look at it at 1%, 5%, and then what? 10%. So not until 10% is also rejecting it, right? Or not until 10% is also uh, not able to be greater than the p-value where rejection can happen. You don't stop at because of 1%. But most that's what I'm saying. The 10% is sometimes, but in some people in their books or in their papers, when it's 10%, they don't interpret the results. They don't see it as strong enough because there's too much room for error. So some people will stop at 5% and still and tell you that the result is statistically not significant. They can do that, right?
Okay.
Because they feel 10% going ahead and making conclusions on 10% is too much of a risk. You understand? So Musa Dankwa will do his thing, and if his results is statistically under 10%, might come out and say that uh, this is not going to work, right? Because the room for error, if I'm going to base my results on 10%, it's too much chances to take. And the likelihood of whatever is going to happening is going to be very small. So they will be more okay with using 1% and 5% level of significance than 10%. So in some papers, they don't report 10%. They will only report 1% level of significance, 5%, because for that one, they are more confident about whatever results they are getting, and they will not conclude on anything more than 5%. Okay. But
Thank you.
as I said, in some instances, some of the things you see might not be happening under 1% or 5%. Make your story okay to be able to say that the results I'm getting is in favor of all the hypotheses I wanted to test. You understand? Maybe you made a claim that males perform better than females. And so 1% is not agreeing with your statement, right? 5% is not agreeing with your statement. Then 10% is agreeing with your statement. That's a small room of chance for you to just write your results and say that, yes, I also found something. Okay, but the believability is going to be lower because it's under 10%. You get it? So these are what researchers go through whenever they want to bring some conclusions out. They have to base it on statistical rigor of statistical level of significance of 1, 5, and 10%. And the standard, as I said, is 5%. The best is 1%. So that is where you want to be. But if it's not statistical significant under 1%, you take 5% as the standard. It's okay. You don't want them to be 10% because 10% is really something people can argue with you and tell you that there's too much room for error with 10%. So even though you've made this conclusion, I don't buy it because it's too much to risk if I want to go with that and go and act on your recommendations under 10% level of significance. They might not do, but they will do for 1 and 5%, which is normally the standard. Do you get it?
Yes, sir. So, sir, are there instances where maybe okay, let me put it so assuming the p-value ends up being over 10%, for example, what would be the implications for the study?
Let's say you get you get the value to be 0.24, right?
Yes, sir.
As your p-value. Now this is what 24%, isn't it?
Yes, sir.
Yes. So 24% is 1%, 10%. So clearly your conclusion is accept the null hypothesis. You understand? So that's going to
Yeah.
be your conclusion in your work. And
Okay.
you have to tell us what the null hypothesis is, right? And so if we are going with what we are doing now, so the moment I see my p-value to be 0.24, I know that my result is saying that there's no difference between the two groups, between sugar and no sugar, or between male and female.
Okay. Mhm.
Sir, please, what if the p-value is more than 10%? What conclusion can we draw from that?
And and there's a clear difference between these two. Analysis can bring this forward.
Hello, what's up? The lecture is off or what? Or my
I
network?
think we lost him, but
I
I'm
think
sure
the
you.
lecture is awful.
Because the line has been
The
breaking out in my end.
Charlie, the network today there is bad. Hey,
Because at my end I
I'm
cannot
struggling.
hear anymore.
All right, so I went off a bit. Okay. All right, so when you have 0.24 as we were explaining, it just clearly tells you that statistically. So the difference between going to do a quantitative analysis and doing a qualitative analysis, some of these things, right? And so statistically, these things that you are seeing, right? It can be that one group, the mean is, let's say, 3.5, right? Now, qualitative higher maybe performance in terms of their CWA, cumulative weighted average, than males, right? That's what the qualitative person will say because that's what they are seeing, the numbers, right? They are seeing that they are describing as it is. But you, the quantitative work, will have to go a step further than what you are seeing and prove what we are doing right now. And if your p-value, for example, was 0.24, which comes to 24%, which is greater than 1%, greater than 5%, greater than 10%, you are going to say that there is no difference between the 3 here for males and the 3.5 here for females. They are the same in terms of statistics. They are all the same. So males are not performing better than females, even though one is 3.5 and the other one is 3. You understand? So that is how statistical work or sort of comes in whenever we are doing some of these things. It puts more rigor and not just on the face value as we see it. So you are not just reporting as you see it, you are reporting based on statistics, based on sample data, and you can generalize for the entire population. That is the whole point of this, right? And so that is how some of these things are interpreted, okay? But the bottom line is what I've given you. We always compare the p-values against the significance levels, 1%, 5%, and 10%. And the rule stays the same every time. The rule is that your p-value, right, if it is less than your significance, right, down, and that is your rule. Anytime that you are comparing the probability values and your alpha is another t-test. This one I'll just quickly, because I've already explained works, right? And so in terms of this one is coming from, the first one was from SPSS. This one is coming from another software called Stata. Okay, and so this one also is testing between two groups, right? So here we have group 1 and group 0. As you see, the observations were this. On the surface, the difference between 21 and 22, well, there's some difference, and this is the difference, right? Negative 1.75. There's some difference there. But the statistical way to look at it is that we look at the middle here. Okay. So the null hypothesis is saying that there is no difference. So the difference is equal to 0, right? And the alternative hypothesis, which we have specified here as HA, the computer or the software, right, not equal to 0. It's an exclamation mark equal to 0. So it's not equal to 0. So that is the alternative. It means that the HO in this instance here HO is the difference 0. Oh, the difference is equal to 0. Okay, and then the HA is saying that the difference is not equal to 0. That is the same as we have already done. So this is here is the probability value. So TP value that's those that 1.28, but the percent and also greater than what? Internet is really disturbing. All right, so this one gives us 16%. 16% is greater than 5, 1%, 10%. So the rule of thumb was that if the p-value was less than the alpha, reject, right? They reject HO. Okay. So what will be our decision? Are we able to reject HO?
We accept.
Are we able to reject HO? HO what? So we accept. So it was that the difference was equal to 0. So it just tells us that once we cannot reject HO, we just have to go and assume that there is no difference between group 0 and group 1. And that's how we interpret some of these things. So it's not coming out from anything. It's just getting the concept and the rules in place, and you can easily base on that and then make your points. Okay, let's look at the chi-square. I remember I told you with the chi-square test, it is looking at two categorical variables and finding out if there is any relationship between them. Okay, so for example, if you want to look at males and females as one category, and then another category as a marital status, right? Now, the frequencies that happen from there, we can find out. Are we having some correlation, some relationship between the number that is male against a particular kind of marital status, or it is fairly distributed? Okay, if it is fairly distributed, you realize that there's not going to be any relationship. But if there is not it is not fairly distributed, but it's probably bulked in one area than the other. Then it's going to bring some significance there. Let's look at this example, right? So we are looking at repair records and then whether the car type is the domestic car or a foreign car. Okay. These are the frequencies from our data. Okay. Now the categories of 1, 2, 3, 4 is the repair record. So maybe you came once, twice, 3 times, 4 times, 5 times. Okay. And so you can say that 48 cars were domestic and 21 cars were foreign. Okay. 2 domestic cars came once in terms of their repair record. 8 domestic cars came twice. 27 domestic cars came 3 times in that order, right? For the foreign cars, no car came one data that you have gathered. This is the sort of frequencies that you have. Now, all we want to bring out here is that, are we having a fair distribution in terms of the frequencies we have here? If it's going to be fair, then if I see domestic cars report 2 times for 1 time, 2 cars come 1 time to repair, I should see maybe 1 car from the foreign as well, right? If 8 cars came 2 times for the domestic, I should see maybe 7 foreign cars as well. Okay, look at the 27 cars reporting 3 times. I should probably have seen maybe 25 times for the foreign cars as well. Then we are talking about a fair distribution in what? The data that or the frequency that I'm gathering. But this is not the case. What I'm seeing is that for the 3 times records in terms of the repair times, I see 27 for domestic. I see only what? 3 for the foreign cars. So the distribution is not that fair. So it's just telling you that if I'm supposed to look at the relationship that exists between these variables, right? It gives me, let me put the null alternative here. So here, the null hypothesis, which is the HO, is saying that there is no relationship, right, between the repair records and then the number of times car counts, whether it's domestic or foreign, right? There's no relationship. And the alternative, which is the H1, is saying that there is a relationship, right, between some of the repair records and whether it's domestic or foreign cars, right? And so what we look out for is the probability value. And what do we see this probability value to be? 0.000. And so if you convert to percent, it is just like saying 0%. So if you compare to 1%, 0% is less than 1%. You don't have to even go to 5 and 10 because already it's even less than 1%. So it is very strong. So it's just telling you that you clearly will have to reject the null hypothesis based on the rule we've spoken about and go for alternative hypothesis saying that there is a relationship between the repair record in 1978 and the different type of cars that existed. Okay, so the conclusion will be that there is a statistical difference in the various category of cars, whether domestic or foreign, in terms of the repair records in 1978. And obviously, yes, there's a clear difference in some of them. 27 for domestic as against 3 for foreign in terms of those who came to repair it 3 times in 1978. So there's a clear relationship. It's obvious. And so that is how the same hypothesis testing rules are applied in the chi-square tests, for example, which are categorical in nature. Okay, so that is something that you might also want to have a look at. The rules do not change. You just have to apply it whenever possible.
Sir, I have a question.
Yes.
So in formulating the null hypothesis and maybe the alternative, without the benefit of the p-values and all that, how do we do it so that we get it right? Because assuming one formulates it by saying that there is a relationship, and then the alternative being there's no relationship, the outcome.
Yeah. So every test has its own null and alternative. You need to find out. So if I want to use a t-test, it has its own null and alternative already. It's not you that is going to formulate it. If you want to use a chi-square test, it has its own null and alternative already before you apply. So if you want to use an F-test, it has its own null and alternative already before you apply it. So based on that, so if you say I'm going to use a t-test, it is not you that is deciding that the first one is no difference between the groups and the second one is difference between the groups. It's already that is what the t-test is supposed to measure. You understand? So before you use any test, read around what its null alternative hypotheses are, and then use that to reflect your own work or objective that you want to establish. You get it?
Okay.
If the t-test is measuring no difference between the groups and difference between the groups as an alternative, then in your hypothesis, in your work, you can state that the null is that there's no difference between the groups you want to test, and there's a difference between the groups you want to test as the alternative. And you follow just as the hypothesis or the test you are going to use has agreed. Does that make sense?
Yes, thank you, sir.
Yes. So it's not you going to determine how to formulate it. Every test has its own way of formulating the test. So you just apply your objective to that way that it has specified. And then you follow suit based on the result that comes at the end of the day. Okay, so if you want to test between any two groups and you want to use a t-test, the rule is that the first HO is there's no difference between the two groups you want to test, and H1 is that there is a difference between the two groups you want to test. So statistical analysis will be done. The p-values will tell you whether to accept HO or reject HO. And then that's it. You follow it like that.
Thank you, sir.
All right. Okay. Let's look at regression analysis. And it follows a similar pattern, the same way we are doing this hypothesis. Regression analysis is also a hypothesis testing. All right. And so, by the way, if you want us to break, we can break for some 30 minutes. When we come back, we finish up. The first session should have ended like 3. So if you want us to break for the 30 minutes, we can do that. If you want us to continue and complete, we can continue. What are you people saying?
Yeah, I think we can continue. That's my opinion. Anyway.
Oh, please, let's continue.
Okay.
I suggest you continue, please.
All right. Okay. So let's continue, because once we break, some of the fundamentals might vanish somewhere. And because it's a similar thing you're about to apply. So it's good it's fresh here and we can apply it as well. Okay, so let's continue. When we talk about regression analysis, it's also another way to quantitatively do data analysis, right? We have the simple linear regression analysis, we have the multiple regression analysis, we have logistic regression, we have multinomial logistic or probability regression, and so on. Now, this class is not supposed to go into the nitty-gritties of some of these, how it works and all of that, but I just decided to expose you to it so that you are able to, at least when you start reading on those sort of things, you get to know. You are going to do econometrics, right? Right. So those are where some of these things will be spoken into deeper Yes, so that you are familiar. So I'm just going to just say a few things and then we move on to what we need to understand. Okay, so when we talk about regression analysis, we're just talking about you finding a relationship between two variables or two or more variables, right? And so normally what our interest is in terms of regression is that, for example, you have a variable y and you have a variable x, and then you want to find out if there is a relationship, and the relationship is measured by something called a coefficient, right? And then we can also have maybe, let me put here as alpha plus beta x plus what we call the error term, right? So if you have two variables, you can want to find the relationship that exists between these two variables. You want to find out. So that's why normally when you are bringing out a topic, we ask you to make sure that there are two variables that are related. One is affecting the other. So let's say the effect of or the effect of, say, learning, the number of hours you learn on your performance, right? Let's use those two variables. So our interest is in the number of hours you learn and how that affects your outcome in terms of CWA, which is your, so it is me measuring CWA as a function of, right, my hours that I learn. So already in my head, I know that if the hypothesis here is that if I learn for more hours, I'm supposed to do better in my performance, which is my CWA, isn't it? So it can be done through a regression analysis, right? And so the simple linear regression analysis will specify it in this manner, where my beta here is measuring the coefficient, or is measuring the relationship between x and then the y. So my x is my number of hours I learn, and my y is my CWA, which is my performance. So that's why we're saying that to do a quantitative work, all your variable has to be measurable. So my number of hours can be measured. So I ask each and every person or student, how many hours do you learn in a week, in a month, in a year, in a semester, whatever it is. I get the value. What is your current CWA? I'm having 3.7, 3.5, first class, second upper, whatever. I list that as well. Now I put them in my analysis and then it brings out the results. Now the results can be maybe 0.3x. So the software is going to measure this beta for me, right? And assuming the beta has given me 0.3x, what it's telling me is that if I increase the number of hours I study by 1 unit, it should increase my CWA by 0.3 units. That is the establishment I have here. And that's what's going to be my conclusion at the end of the day, that I saw a positive relationship between the number of hours I learn and then the CWA I get. So if I get the results to be plus 0.3x, the positive nature is telling me that if I increase the number of hours I work, it also increases the CWA. That is the relationship I have found. And I can do this through a simple linear regression analysis. Okay. And so that's what regression is supposed to do. You have two variables. You are trying to understand one variable from one other variable. So the effect, normally when you are setting your topics, the effect of this on this, that is all you want to find out. How is the effect measured? Is it a positive effect or is it a negative effect? Assuming I did this and I got negative 0.3x. Now negative is telling me that if I increase the number of hours I learn by 1 hour, I reduce my CWA by 0.3 units. So what is it telling me? Then I shouldn't learn more hours. Maybe learning more hours goes to affect the brain and you don't capture a lot in your head, you can't do well. So it's better you learn in small hours, right? So that is what the results is likely to have told me. Okay, so the linear regression is just looking at how we have expressed our equation. It's in a linear form, right? We all know y is equal to mx, right, plus c. In our senior high or O level or A level, whatever we did, this was what we learned. That's a linear equation, right? So every line of it, the equation of a line is giving us this. And it's the same thing that this regression is giving me. The bx here, or beta x here, is the mx here. The alpha here, which is a constant, or the intercept, is the c here, right? And normally we say the c-intercept, or the y-intercept, or whatever. The alpha, or the constant, is measuring when you are not having number of hours there. When our number of hours is equal to 0, what is your CWA? So if you are not learning, we are learning 0 hours, what will be your, whatever it is, your CWA will have a value. And that is what the alpha or the constant will measure. And that's why we normally call it a y-intercept. When you are drawing your graph, you see that it starts from a point on the y-axis. So if x is equal to 0, y is still having a value. So if your number of hours is equal to 0, your CWA is not going to be 0. It's going to start from somewhere. It's going to be some value, right? And so that is a linear regression, okay? A multiple regression is just saying that instead of us having one variable, we have multiple variables to explain our y variable. Okay, so in that instance, it's going to be y is equal to alpha plus, say, beta x plus sigma, let's say, z plus the error term, right? And so now we have one variable, two variables, explaining the dependent variable y. And that's what makes it a multiple regression analysis. That's all. That's nothing else. So simple linear regression is just one variable. Multiple regression is talking about multiple variables. Okay, that is the meaning. Okay, now let's look at logistic regression. Logistic regression is also a regression analysis, all right? But the outcome, okay, the y variable here. So with the linear and the multiple linear regression and the things we are talking about, this y outcome here is a continuous variable. Now you understand why we are coming from with a continuous variable and discrete variables and stuff like that. Now, with this particular one, with the linear regressions and the multiple linear regressions that we are talking about the y or the dependent variable being a continuous variable, like income, like age, like CWA, or your cumulative weighted average, or whatever it is. They are continuous, okay? Or it could be discrete, but then it follows with numbers. So discrete, continuous, they are all quantitative variables, right? That's what we use for this type of regression. Now, if you come to the logistic regression, the outcome variable y is a categorical variable. It's like a qualitative variable. So it can assume, just say 1 and 2, or say 0 and 1, right? Let's assume yes and no, those kind of variables, okay? So I want to predict you coming to school or not coming to school. So absent or present, okay? And if I say absent or present, if you are present, I mark you 1. If you are absent, I mark you 0. So my dependent variable takes the value of what? 0 and 1. And that is what our logistic regression, so if that is what your dependent variable is, then you cannot just use any kind of analysis or regression analysis. You have to go and use the logistic regression analysis. So knowing your dependent variable and how you have measured it can get you to the level or know what kind of analysis you can do. Okay, so we don't just do any analysis at all. You just have to know the kind of variables you have and how you need to measure it, and then the kind of regression that you can use. Okay, so logistic regression, anytime you hear logistic regression, it's just saying that you are predicting the outcome, which is a binary outcome. Okay, it's just two, yes and no, absent, present, married, not married, working, not working. If that is the way your dependent variable is, or your topic, okay? So investing, not investing. I want to maybe, what is the effect of so and so on investment decisions? The investment decision is what? I invest, I don't invest. And what are the things that are predicting if somebody is going to invest or somebody is not going to invest? You need to look at it from a logistic regression point of view. Okay? Working, not working. What are the predictors of somebody being in the labor force or not in the labor force? Okay? Maybe being married is one, being female is one, level of education is one. All of these can be used to explain whether or not somebody is working or not working. So the predicting variable here is what? A binary outcome. Then you use a logistic regression. The fourth one is multinomial logic or probit. This is where your outcome variable is more than two categories. Okay, so I can have a y outcome or my categorical variable being maybe 3, right? Which network are you with, or what are the factors that influence the network that you go to choose when you want to buy a SIM, right? So I can use Telecel, which is one outcome. I can use Airtel Tigo, which is another outcome. I can use what? MTN, which is another outcome. Now this goes beyond what? 2 options, right? So Airtel, this can be 1, this can be 2, this can be 3. Or when you're doing the analysis, you don't start from 1. So you can start from 0. There always has to be a 0. Then it starts from 0 to 1, and then to 2. So these are 3 categories that are available. And so I cannot use a logistic regression, which only can look at only 2 outcomes. I need to go and look at multinomial, right? Multiple. So I use that multinomial logistic analysis or probability analysis. And that is what can be used. You get it. So everything you're doing has a reason, and it also will help you go to the kind of methods that you can use in the analysis. So don't just follow people did this, I want to do the same. Are the variables similar to what you have? And does it make sense to do exactly what they have done before you go ahead and do it? Okay, so these are the sort of differences that exist. Okay, any questions on this expose before we move on?
So I don't know if it's being recorded because of the interruptions.
Yeah, I think it is.
Okay, thank you.
All right, so this is a simple linear regression analysis, right? You put in your data, and then it comes out with this result. This is coming from its data results, right? And so every regression that output accounts looks similar like this, right? These are the sort of things you look out for. So I said y was going to be equal to, say, alpha plus beta x, right? The y is your dependent variable, and the x is your independent variable. Independent variable means that they are the ones you are using to explain the dependent variable. Dependent variable is depending on the independent variable for its meaning or explanation, right? And so these things you see here as coefficient, they are the alphas and the betas, right? The alpha and the beta, they are the ones we are calling the coefficient. So that is what the regression results will measure. or bring out. Okay. Now pay attention. This constant here you see underscore CON is called a constant. That is the intercept. And so alpha here is being measured by this constant. That is if x is equal to 0. The constant, this is the value that you get, negative 2 point blah, 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 blah. And then the beta here is the other one that has been measured, this one, the time underscore TV. That is the beta. So the regression coefficients are the alpha and the beta, and that is what is always explained or given you in terms of the values. And now you will have to go ahead and interpret it as to how it fits into your work, right? And so the same way, assuming that your Y is your CWA, you want to see how CWA is affected by your alpha plus your beta H, which is your number of hours that you study. So let's assume this is what we have done here. Okay, so let's look at the coefficients. Alpha first, right? Alpha is a constant. It is giving us negative 2, blah, blah, blah. So what does it mean? It means that if you don't study, if hours of study is equal to 0, your CWA, because it's negative 2, CWA will reduce by negative 2.134777 units. Simple as that. If hours of studying is equal to 0, because it's your constant, your intercept, your CWA, which is your performance, that is how you measure your first class, second upper, and the rest, will reduce by negative 2.0, blah, blah, blah. That's the meaning. Simple as that. Now let's look at the beta. The beta is the coefficient of the number of hours you study. And so because we measured it in hours, we can interpret it by 1 unit change. 1 unit change is 1 hour, right? So we can interpret it as if the hours that we study increases by 1 hour, right? Based on how we measured it, I tell you we are measuring it in hours. So if it increases by 1 hour, what do we see the coefficient as? It is positive. And it's what? 0.0440, blah, blah, blah. So if your hours of study increases by 1 hour, it is going to increase your CWA by 0.044069 units. Okay, because it's positive. That is why it is reflecting a positive an increment. 1 hour increment will result in 0.044 blah, blah, blah increment in your CWA because it's positive. If it were negative 0.4, then it's going to say that if you increase the number of hours you study by 1 hour, it's going to reduce the CWA by 0.044091 units. That's the interpretation. I hope I'm making sense. Let's get that first before we move into something else. So anybody that don't understand what I'm doing in terms of how we are interpreting the coefficient. If it's positive, it is an increase. If it is negative, it is a decrease or a reduction in the y variable, which is a dependent variable, right? So your y variable. So any positive coefficient will increase the y variable by how much you have there. And any negative coefficient will decrease the y variable by whatever value you have there. Okay, now let's come to our significance. Okay, so our significance, like we have done in the other ones, let's look at it. So before anything, let me put down the rule again. So the rule was that we look at the p-value. If it was less than the alphas, we rejected the H4. Yes, that's what the rule is. Now, when we come to regression tables analysis, this is your p-value. I hope you see it. It's p greater than t, right? In your regression or tables, that's why you see. You either see p greater than t, you can see p greater than z, depending on the distribution that you use, whether it's a t distribution or a a z distribution or f, it can be p greater than f, right? And you see that you put these things there, right? So the p is just telling you that this column is the probability values, this one. And what do we compare with? We compare with 1%, 5%, and 10%. So let's look at this one we said is the beta, right? And this one we said is the alpha, the constant. So let's start with the alpha. Alpha gives us a coefficient of 0.242. Yes, who can tell me what we do here? Do we reject the HO or accept the HO? Yes, if the p-value is 0.242, what do we do?
We accept.
We accept because this is 24.2%. It's more than 1, 5, and 10. So we accept the null hypothesis. Now, the question is, what is the null hypothesis in this scenario? Now, this is the null hypothesis. The null hypothesis in any regression analysis, when you are measuring the coefficients, is saying that alpha is equal to 0, and the H1 is saying that alpha is not equal to 0. Okay, so if you say you accept the alpha, what does it mean? If you accept HO, what does it mean? It means that the coefficient, which is this negative 2.134777, is actually not different from 0. So if a variable is actually saying that it is equal to 0, does it have an effect on your coefficient, on your dependent variable? No. So in this scenario, you don't go and waste your time trying to interpret this coefficient here, alpha, because statistically, this negative 0.2 blah, blah, blah is the same as what? 0. So forget it. It doesn't affect your dependent variable in any way. Full stop. Let's look at the second one, beta. The beta is 0.0000. If you convert to percent, is what? 0%. Now, what will be your decision for a 0% p-value? Yeah, what will be your decision? Comparing that to 1, 5, or 10%?
We reject.
You reject, right? So once you are going to reject, now the same thing in terms of your HON. So you're just saying that beta is equal to 0, and then beta is not equal to 0. So if you reject this, then you go and accept what? This. And when you are accepting H1, H1 is saying that the beta is not equal to 0. So statistically, the value you see here as 0.04400691 is actually 0.440691. Then it gives you the go-ahead to go and then explain how it affects the dependent variable. And we already have done the explanation that if the hours of studying increases by 1 hour, your CWA is going to increase by 0.440691. And this is statistically significant under even 1%, because the p-value is 0.0%. So it tells you that it is a very strong conclusion you have, because statistically it's even under 1%. So when you are making conclusion about this particular variable, you are very confident that even under 1% level of significance, when you increase the number of hours by 1 hour, the number of hours you study by 1 hour, you are most likely going to see an increase in your CWA by 0.04400691. Okay, that is how some of these things are done. All right, and it's all probabilities. It is all about hypothesis testing, and we go on and on to interpret. Okay. Now, these things you have here on the regression results, right? This one here is just regression characteristics. It talks about number of data you have. So here, number of observations were 100. So you collected data on 100 people. Now, this F you see here is also talking about whether the whole significance of the model you have makes sense, right? So the Y is equal to alpha plus beta X that you stated or formulated. It wants to look at if this whole model here even makes sense in the first place. And that is captured by this one here, probability greater than F. It is also a hypothesis testing. It's also testing the hypothesis that your alpha is equal to beta and it's equal to 0. It's saying that all your coefficient is equal to 0. That is H0, right? So your H0 is saying that all your coefficient, alpha, beta, they are all equal to 0. And the H1 is saying that at least, right? At least one of the coefficients is not equal to 0. So it's either beta is not equal to 0 or alpha is not equal to 0. So long as one of them is not equal to 0, that is your H1. But the H0 is saying that all of them are nothing. So it means that the whole model you are running is nothing. Just throw it away. It doesn't make sense. So this probability greater than F is measuring whether or not you have to go ahead and even go and look at the coefficients you have in the model or not. So we call that the overall significance of the model. And what can we talk about this? Look at the p-value, right? It's 0.0001. If you bring it to percent, it's still 0.01%, right? So it is under 1%. 1% can even, you can still work with it. So once it's less than 1%, you can easily reject the null hypothesis. So we can reject this null hypothesis saying that all the coefficients are equal to 0 and go and accept the H1, which is saying that at least one of the coefficients is not equal to 0. Once this is done, then you can be confident that the model you are running is making sense. So there are instances where the whole model does not make sense. So what you don't even get anything to explain. It means that you did not do a good job in terms of modeling the model that you have. Okay, so you look out for those ones as well whenever you are doing your analysis. Okay, I'm sure you get to do more of this in the econometrics and then the applied part of it where you do some of these things, how you do this to get results like this and stuff. Okay, so this is just an opener. Don't stress too much. Now we have these ones as well, R square. It is also there in your econometrics. You get to know what R square is. Okay, it just also measures how well your independent variables are helping you explain the dependent variable. So in our case, how well is the number of hours you use to study helping you explain the changes in your CWA? Okay, so that is what the R square measures. So the higher it is, the better the explanatory power. So this one here is 0.14, it's 14%. So it means that your number of hours you study can help explain your CWA by only 14%. So there's more variables out there that can help you explain your dependent variable, which is your performance in school. So then you have to add other variables there to really do a good job, right? But only 14% for the hours that you study, which is quite significant, right? So these are some of the things you see in regression analysis, right? This one on the left here is an ANOVA result. But I won't go into it. Every regression that you do or run, you see this ANOVA results, this one here, right? So this one here, right? So ANOVA is just analysis of variation. So every data that you gather, what regression analysis does is that it uses the analysis of variation. It finds out how different one person is to the other. And it uses all of that to bring about some of these coefficients we are seeing here. Okay, so ANOVA is sort of a subset of regression. So for you to get the regression results out, it goes through ANOVA or analysis of variance to bring it out. And I'm sure you might handle those things in the econometrics here and there to understand it better. Okay, so this is a simple linear regression result. And you see that it's similar to the explanation we did for our categorical chi-square t-test, because it's all hypothesis testing. And so in quantitative analysis, hypothesis testing is very critical because everything we get is based on that. Okay, this is an extended version. This is a multiple regression where the coefficients are more than just one, right? And you see that it presents the similar thing as you saw, right? So you have your ANOVA again here, right? And then you see that this one has presented the regression parameters, the things you did. So 100 people were interviewed. You see the probability greater than F, which is measuring the overall significance, right? This one is 0.00. It tells you that it is highly significant. So it means that the model is good. So another thing you can use to see some of these things is that the closer it is to 0 in terms of the p-values, the better it is. So if you see 0.0000, you don't have to think through, let me go and compare and reject HO. You already know that you are rejecting HO, right? And so if you go to this and you see the p-values here, look at these p-values. You should be very happy when you do a regression analysis and you see some of these p-values, right? Highly significant, under 1%, highly, all of them, right? It is only this one. This one is 1, 2, that is exactly 1%. So this one is not significant under 1%, but it's significant under 5%. Okay, because it's exactly 1%. So it's significant under 5%. Those are how you interpret your regression coefficient. And look at this. The negatives are all going to reduce your coefficient, your dependent variable, right? And the positives are always going to increase your regression dependent variable. That is how it is measured and interpreted. Okay. So one last thing to talk about here. Now, if the variable is quantitative, age, weight, heart rate, these are all measured quantitatively. So then you interpret it like I've already interpreted for you, right? If it increases by 1 unit, it affects this one here by the coefficient that you see. Okay, so if age increases by 1 year, assuming you are measuring your age in years, if weight increases by 1 kilogram, assuming you are measuring your weight in kilograms, if your heart rate increases by 1 whatever, that is how you are interpreting your or measuring your heart rate. It is going to reduce the coefficient here by negative or so and so. It's going to reduce it by 0.11, 0.38, or 0.16, blah, blah, blah. That's how you interpret it. Now let's look at this. Male. Okay, male is a categorical variable. So you're either male or female. So what they have put here in this here is male having the value of 1 and female having the value of 0. So this is male and this is female. So whenever you want to use a qualitative variable in a quantitative analysis, we call something a dummy variable. Now you have to convert your categorical variable into a dummy variable. And by dummy variable, it's just saying that make the main one you are interested in 1 and any other category that is left 0. The 1 in there is going to be the presence of the characteristic, and the 0 is going to be the absence of the characteristic. That is how come you can do a quantitative analysis if you are using a qualitative variable. So if it is marital status, married can take the value of 1. All the other categories will be take the value of 0. So single, divorce, they are all going to be 0, whilst married will be 1. So when you are interpreting, it is the characteristic of being married, and whatever results you are getting is because of the fact that you are married. That's how you are seeing that, whether it reduces your dependent variable or it increases your dependent variable. That is how qualitative variables are used in quantitative analysis. You work with what we call dummy variables. You can write it somewhere, read on it later on, but that's how it works. It is a variable that has 1 and zeros. We don't have 1, 2, 3, 4, 5. No, it is 1 and zeros. The one that sees the value of 0 are all going to be the absence of the characteristic. The one that have the value of 1 is the present of the characteristic. So in this analysis here, you see male. What it means is that it is male that was the presence characteristic, right? The absent characteristic is female. And so when you are interpreting this, you interpret it in the form of being male. Is it positive or negative? It's positive. Increases, right, the dependent variable by 13.20789 relative to being female. I'm taking it again. If you're writing, you can write. So if male is the present of the characteristic, then as you see it like this, it's going to be stated that being male, that is having the characteristics of a male, if the coefficient is positive, right? Here is positive 13.20. You interpret it as being male, because it's positive, increases the VO2 max, which is your dependent variable, by 13.20788 units. Okay, that is how you interpret it. If it's negative, you could have said that being male reduces the coefficient, the dependent variable by 13 point blah, 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 relative to being female. So that is how you interpret what we call dummy variables, using categorical variables or qualitative variables. Okay. You can read more on these later on. When you want to, you go to YouTube and say, how do we interpret regression analysis coefficients? They will tell you exactly as I'm saying. So you can have more information on that there.
So if you can go over that interpretation for the last time. So sorry about that.
The male.
Yeah, I said being male increases the.
Yes, it's increasing because the coefficient there is what? Positive.
Yeah.
The characteristics we are interested in is being male.
Yeah.
So in your data collection, when you are collecting data on gender, you say male, right? 1. You say female is what? 2. You can't put 1 and 2 here in the regression model. It won't work. So when you want to put a categorical variable in a regression analysis or quantitative analysis, what you do is that you need to define which of them do I want to interpret. Is it being male or being female? Okay, I want being male. Okay, so if being male is equal to 1, let me leave it as that. But being female cannot have the value of 2. I need to change being female to 1, 0. So this is what you do before you do your analysis. So your variable male will be represented in there as 1 and 0. The 1 is being male, means that the present of the characteristic, that's why I've given it the value of 1. It's just like computer analysis. You have zeros and ones. The ones are what tells you that this is what is needed. The ones that are 0 are telling you that, yes, it's absent. We don't need the females there. So all the analysis is going to run on being male because it's the one that is having the value of 1. And this is what we are calling the dummy variable. So this variable male here is having the value of 1 and 0, where 1 is for male and 0 is for female. 1 is the presence of being male, 0 is the absence of being a female. So the interpretation is, once it's positive, we are saying that you interpret it as being male or having the male as a gender. Is it positive? Yes, it will increase your dependent variable here by this coefficient that you see relative to being female. That's all.
Thank you.
Okay. So and these are the only ones you will see. It's either a qualitative variable that you have in there as your one of the variables, or a quantitative variable that is in there as another variable. So it's either you are combining qualitative, quantitative in there, or you have all quantitative. So it's just a mixture of these that you normally will see in a regression analysis. Now, this is a logistic regression where I said that your dependent variable is either 1 or 0, right? Just two options, 1 or 0. It brings the same information as a regression, any of the regression results. And remember, we are dealing with still our p-values, right? You see that this time around is z. So the distribution in the logistic regression is a z distribution, so it uses a z. So the same interpretation is what we use. You check, are these greater than, are these less than 1%, 5%, or 10%? And then you go ahead. You realize, obviously, this is 11%. It's more than 10%. So you reject, you accept the null hypothesis. This one is 93%. You accept the null hypothesis. It is only this one, the middle one, that is 0.32, which is 3.2%. So it's more than 1%, but it's less than 5%. So you can interpret the middle one, and that is the best you can do. Right? So that is for logistic regression. Another thing I will add here, for logistic regression analysis, you can write it somewhere. Whenever the first thing or output comes on the screen, we don't interpret this coefficient in terms of the numbers you see. We don't. Right? There's another command after this that we interpret. I'm sure you get to know that. Okay, but you don't go and interpret it as we have interpreted the linear regressions earlier on, right? We don't do that. For logistic regression, we can interpret the signs. The first output that comes, you can interpret the signs. This is negative, so it will reduce it. This is positive. It will increase this. This is positive, it will increase it. It's okay, just that. We don't go and interpret the 0.049, no. We have something called the marginal effects, MFX. Okay, so after this output comes, we put another command which brings about another result, which is the marginal effects. Those are the ones that you interpret the coefficient, not the iterations output that you see. We don't interpret that. We can interpret the sign, right? The sign, negative, positive, is okay, but not the magnitude. Right. That is also another thing that I can put across, just in case you don't meet it anywhere and you need to do anything analysis on that. Okay, the multinomial logic regression. So that also, it follows a similar interpretation, right? And so you get to see that it also comes with p greater than z, right? So all of these are your p values. So they are the ones that you look at and then find out if you are going to reject some or not accept. So you see that I'll only take the ones you are going to accept. So you see this 0.00 is clear. These ones are going to reject the null hypothesis, right? So you're going to interpret all of these coefficients. This one here, you interpret with care because it's under 10%, right? 0.067 is 6.7%. This one, more than 10, you don't interpret. This one, more than 10, you don't interpret. Okay. So I'm sure by now you are getting familiar with some of these. Okay. All right, so the ANOVA bit, as I said, this is where we also want to find out if there are differences between groups, but the groups are more than 2. Okay, so the t-test that you found, you realize that every time we're looking at 2 groups, so either it's a male and female variation, or group 1 and 0, only 2. So t-test is meant for only 2 groups. Now, assuming I have 3 groups, say morning, evening students, and I have weekend students, right? Now, these are more than 2 groups. I cannot use t-test to do this. So if the CWA for this is 10, evening students CWA is 14, and then weekend CWA is say 12. If I want to find out or test whether there are differences between the CWA for morning, evening, and weekend, I cannot go and use the t-test. Why? Because the groups are more than 2. Whenever the groups are more than 2, we use the ANOVA. That is why we use the ANOVA. So if it's just morning and evening, there are only 2, I can use the t-test. Evening and weekend, there are only 2, I can use the t-test. But at the moment it becomes morning, evening, weekend, I only have to use the ANOVA, because that is what can go beyond 2 groups. So we're comparing means of 3 or more groups, then we use the ANOVA, right? So we have various two forms, a one-way ANOVA, and then the two-way ANOVA, all right? So the two-way ANOVA is more of an extension when we are looking at 2 variables or 2 independent variables, if it has an interaction or not, right? You see that here, CWA is only 1 variable, right? And that's why we use one-way ANOVA. We are finding between 3 groups for only 1 variable. But if you want to find out between 3 groups for 2 or more variables, we use the two-way ANOVA. That's basically what it means. So examining the effect of steady method and steady environment on test scores. So the test scores is the variable we want to find the difference between the groups, but we are looking at coming from the steady method and then the steady environment. How does the steady method affect the test scores? How does the steady environment affect the test scores? And that is what brings about the two-way ANOVA that we are looking at. So ANOVA is used to compare means of 3 or more groups, whilst t-test is used to test for the difference between only 2 groups. Full stop. So those of you who want to do any topic that is around comparing means or comparing a particular variable among groups, yeah, t-test or ANOVA is what you can use to do that. Okay, we can also do correlation analysis. Correlation analysis is just finding out if there's a relationship between variable A and variable B, right? And we have 2 of them. One is the Pearson correlation analysis. Here, we look at it from between 2 continuous variables. So here we are talking about maybe income, which is a continuous variable, and maybe the number of hours you work, right? These are all continuous variables. So we want to find out, is there a relationship between the income you get and the number of hours you work, right? And so we can get a positive relationship or a negative relationship. Positive relationship means that if I work more hours, I have an increased income, right? A negative relationship means that if I work more hours, I have a reduced income. The direction is the opposite. That's the correlation, right? So correlation analysis between study hours and exam scores, okay, like we have been doing right now. So we can either do a regression analysis on this same topic, correlation, the effect of study hours on exam scores, or we can just do a correlation between study hours and exam scores. Okay, correlations are only going to tell you there's a relationship, positive, negative, a strong or a weak relationship. But the regression is going to give you the by how much. That is the coefficient that we measure. Okay, so those are the differences. Correlation is sort of on the surface, right? We want to find out there's a relationship, positive, negative, strong, weak, moderate, that's all. But the regression will tell you that, yes, there's a positive relationship, but the relationship is by this much, 0. This, 1.5, whatever it is. It gives you some magnitude that you can use to add as well. And then the Spearman-Rank correlation coefficient is used to measure the strength or the direction of relationship between two ranked variables. You have to have the ability to rank the variable, right? So assuming I have a Likert scale, and then I measure it as superior, right? I measure it as good. I measure it as average. I measure it as bad, and so on. Okay, so assuming that I have a variable like that, this is a form of a rank, right? So I can give this 5, this one will be 4, this is 3, this is 2, and so on. And another one, maybe on a scale of 1 to 5, how would you rate the consumption or the satisfaction you got from a particular commodity, right? So I can also measure it. Oh, this is rank 5, this is 4, this is 2, this is 1, this is 3. Now, once you have two categorical variables like this that are in a rank form, you can find the correlation amongst the variables. So you want to find out, is there a relationship between the satisfaction I get from consuming a particular kind of car? Okay, so if the car can be categorized as superior, good, average, bad, poor, right? And I am able to have a rank of 5 or whatever I put to that particular cars, then I can find out that there's a relationship, positive relationship between how my consumption, my satisfaction level is and the particular kind of car that exists. So if it's a positive relationship, it tells you that the higher my satisfaction, the higher or the better the car that I have, all right, or that I use. And the lower the satisfaction I'm ranking, the lower the particular kind of car in terms of superiority. Okay, so it doesn't always mean that you have to do a correlation analysis on only quantitative variables. You can do a correlation analysis on qualitative variables as well, so long as you can rank those qualitative variables. So what we use here is called the Spearman's rank correlation coefficient. So there are so many things you can do in your analysis. Depending on what you want to do, you just find the tool that can help you do that. Okay, so that is for correlation analysis. And for correlation analysis, it also has the same way we do the hypothesis testing, right? This is an example of a Pearson correlation analysis in SPSS, right? Do you see the stars? As I was explaining to you earlier on. So correlation is significant at 0.01 level of significance. This is 1%. So if it is 2 stars and you see 2 stars on the variable, it tells you that statistically it is significant. So if it's a positive relationship, it is actually a positive relationship. If it's a negative relationship, it's actually a negative relationship. And it's also saying that your HO for this correlation analysis is that there is no correlation, right? And the H1 is saying that there is correlation. Okay, so that is how correlation coefficients are also measured in terms of its hypothesis that you test. So for those who want to do correlation analysis, right? Remember, this is your hypothesis. So the hypothesis is that there's no relationship between variable A and variable B. The alternative is that there's a correlation between variable A and variable B. So depending on whatever variable you want to measure, right, and you want to use correlation analysis in your objectives, this is your correlation hypothesis you are testing. And so when this output comes out, right, what you see is that it is the variables here, right, that are also represented here on the top. So it's a row against the column. So if I take reading scores here, I'm finding the relationship that exists between itself, which is also reading score. So reading score against reading score. So you see that the value I have is 1. You see this diagonal, which is they are all giving you values of 1, 1, 1, 1, right? It is telling you that it is the variable against itself. I want to find out the variable I'm looking at, the relationship it has with itself, and it has a perfect correlation. That's why the values are 1, 1, 1. So correlation coefficient ranks between -1 and then +1. Okay. So the 1, 1 you are seeing is just telling you that it has a perfect collinearity in them. It's a variable against itself. So what do you expect? That's the relationship, right? And the others that you see on the other side, these ones, these ones, these ones, these ones are the variables here against another variable, right? So writing score against reading score is what you see here. Math score against reading score. Science score against reading score. Female against reading score. Okay, so if you see it as positive, it tells you that it has a positive correlation. If you see the stars on it, it tells you that you are rejecting the null hypothesis, which is saying there's no correlation, and you are accepting the alternative hypothesis saying that there is a correlation. So if it's positive, there's a positive correlation. If it's negative, there's a negative correlation. Okay. Now, one thing that we also want to find out, if the coefficient is greater than 0.5, then it is a strong correlation. Okay. So if the coefficient is greater than 0.5, whether negative or positive, okay, so 0.5, so it's greater than 0.5, we're saying that it is a strong correlation. If it is less than 0.5, it's a weak correlation. If it is exactly 0.5, it is a moderate correlation. Okay. Now, it goes whichever way, whether negative side or positive side, right? It works in the same way. So if it is greater 0.5, right? Whether negative or positive is a strong correlation, whether strong positive correlation or strong negative correlation. If it's exactly 0.5, whether positive or negative, is a moderate correlation, positive moderate or positive negative moderate correlation. That's how you interpret. If it is 0, then no correlation. If it is 1, it's a perfect correlation. Okay, so let's bear that in mind. These are the interpretations for any correlation analysis. So for these ones, 0.59 is greater than 0.5, so it's a strong correlation. 0.66, very strong. 0.63, very strong. Okay. 0.29, assuming we had stars on it, it was going to be a weak correlation. Okay. 0.12 is a weak correlation, assuming we had stars on it. So the ones with stars are the ones worth interpreting. The ones without stars is telling you that statistically, they are equal to 0. right? Because that's established, that's what we established in the null and alternating hypothesis for correlations. Okay, so these are the few things that we can give you under some of these, right? It's just sort of a bonus here. In effect, this is more on a different course, but I decided to bring it to you so that you get it before you get to where you really do some of these. Yeah. So moving away from that, your data can be put into graphs or charts, right? You can have software tools with Excel, SPSS, Theta, R, SAS, and a whole lot. There are a lot. At least get one of them that you can use. SPSS can run regressions, correlations, and the rest. Theta can do that. R can do that. Get to learn one of them because you are going to run your analysis anyways. Okay. So some key takeaways, right? We are saying that when you're doing tables, make sure, or in your write-up, when you're doing your research work, make sure your tables and charts are all standard and consistent throughout the work, right? In terms of font sizes, in terms of headings, titles, table designs, and the rest. Don't just pick any colors, mix them up, and those sort of things. It makes reading difficult. Choose one style and use it. Font size, font type, they all have to be the same, right? Alignment, align in the center and all of that. Some of you will do an analysis, a table, and present the same information in a chart. It doesn't make sense. Either it's in a chart or it's in a table. Just choose one. Okay. Some output from the statistical software has to be formatted. Don't go and lift like you saw in a Stata like this, right? Don't lift this and come and paste in your work as the results. These will be put on the appendix, right? But then you create a table that reports the coefficients, standard errors, p-values, and stuff like that. Look at how people have done it in their journal articles and stuff, and represent your work in similar manner. Don't just copy and paste as you see it. Like you see SPSS like this, copy like this, come and paste. Sometimes it's confusing. You can create a table, nice table, and have the original one in the appendix. Anybody that is thinking it's not correct can go back to your appendix and check to see the actual results there. And make sure your data that you present as analysis answers your research objectives, right? So that you will avoid all irrelevant tables and charts. Some of you have a lot of questions asked in your questionnaire and present all of them in your work. Meanwhile, it has nothing to do with your research objectives. It wastes a lot of our time, right? So just go straight to your objectives, use the tables and charts that answer your objectives, present them, and then you'll be fine. Okay, it makes sense. Now, this is just a snapshot of the statistical test you can do, when to use it, a description as to explain what it's used to, it does, and an example, right? So you are not found wanting. You can have a look at it, and it can guide you based on the kind of objectives you are setting for yourselves, and then the kind of test that you need to use. I've explained majority of them in this particular session. All right, so go through and see when to use what. As I said, all of you are doing quantitative, whether you like it or not. And so this will come in handy for you. Find a way to understand them if you don't at this stage, so that you are not found wanting, especially when you start writing your work and the method you are going to use, statistical analysis you are going to do, and all of that. You should be able to fine-tune, especially what you did in your midterm, right? Fine-tune and get to where your proposal ends, which is methodology. So all of these can guide you as to what you need to do or include in your methodology before the session is over. All right, any questions for this session before we end it and close for the day? All right, so once there are no questions, my assumption is that some of you get it to an extent. and your work is to sit down and I mean, you have the recording, so ask for it, get it, and then you can go over and over and until you are familiar with whatever we are doing. Okay. So, God willing, we'll meet same time next week to touch on some few others that we have. All right. Yeah. So I wish you all the best in the week ahead and see you soon.
Thank you so much,
Wish
sir.
you soon.
Thank you,
Thank
sir.
you.
Thank you.